Good morning, sir.
Oh, good morning. Morning, Ravichandran. Good morning, Bala.
Good morning, Lakshmanan. How are you?
Good morning, Professor Balakrishnan, sir.
Good morning. I was having some difficulty joining, but it said recording, so that's probably the reason it didn't let me in. Let me see if. Okay. So I'll use a whiteboard and share screen. Just trying to find out what is the command. Am I audible? Can you hear me?
Yes, sir. Hear your voice, sir.
During the talk, I may have to mute my video. I'll share screen, but I'll mute my video so that there's bandwidth. Otherwise, it's unstable, it says. After the talk gets started, then I'll do that.
Okay, sir.
Good morning, everyone. We welcome you all for the third day Science Academies Virtual Lecture Workshop on recent developments in classical, quantum, and condensed matter physics, organized by National College, Tiruchirappalli. We'll start the session. I invite Dr. S. Ravi, Associate Professor, to introduce our speaker.
Can you hear me? Can you hear me?
Dr. Ravi,
Yes, I'm on.
you unmute your video.
Yeah, I unmuted.
Your video is off.
I switched off my video, but I have unmuted my
Your audio is feeble. Please enable your video.
Everything is perfect. Can you see me?
Yes, video is there. Please.
Audio I have unmuted. Can you hear
Audio is feeble.
me? Everything is full. 100% audio I have.
You can remove your headset.
Can you hear me now? Is it audible now? Clear?
You remove your earphone and you try with the laptop directly.
Yeah, I have disconnected the headphone. I'm talking directly now. Can you hear me now?
Audio is not up to the mark.
Can you hear me now? Is it audible?
Is it okay?
Is it okay now? Can you hear me?
Your voice is not audible. இல்ல powering yours sir second. இவங்க அதுதான்
அப்படியே வெளியில பேசிடலாம். Good morning, friends. Is it audible now? I'm sorry. There's a slight. So, friends, the first lecture on this third day of workshop will be given by Dr. V. Balakrishnan. In fact, I went through his CV, and of course, I found that I am absolutely undeserving. I don't deserve to talk about him. Anyway, the two things that impressed me a lot is, which will be much useful for our students and of course for all our staff members. One is, he has given 7 video courses under NPTEL program sponsored by MHRD. This has been viewed by several million students worldwide. This is very important. And yesterday, I am fortunate to listen to one of his lectures. It was absolutely brilliant. And I want all of our students and staff members to humbly listen to his lectures. Those were fantastic lectures. This impressed me a lot. His CV runs to pages. I can say a lot about him and many knows about him. But this one is very important for our students and our staff members. I humbly request every one of our staff members to listen to his NPTEL lectures. It is absolutely brilliant. So the second thing which I was much impressed to watch, he has published a book on mathematical physics. And again, I went through that book. Such a great man of his great caliber has come down to the level and he has written a book so that every one of us can understand. I request all the students to go through that book. I request all the staff members to go through that book. It is very simple, beautifully written by him. So anyway, he has published so many publications. He did his PhD in United States. He did his postdoctoral fellowship in TIFR. He was a scientist in IGCAR. And currently, he is an adjunct professor in IIT Chennai. All these things are fantastic. But above all, for us, these two things impressed a lot. Please listen to his NPTEL lecture and kindly go through his book written in mathematical physics. So with this small briefing, and of course, I don't deserve to talk much about him. Anyway, welcome you, sir, Dr. V. Balakrishnan. I hand over the session to you, sir. Thank you so much.
Thank you very much, Dr. Ravi. And at the outset, let me thank Professor Lakshmanan, Professor Ravichandran, and so on, the rest of the organizers for giving me this wonderful opportunity to talk to you this morning. I must start by confessing that I'm not too familiar with this online mode, and I'm liable to make some basic mistakes and make myself invisible once in a while, but I hope I'll be able to get back before too long. So please pardon me for that. I'm going to write on the whiteboard and share screen. I decided against preparing a talk with PDF slides beforehand because I thought that it would go too fast. And I wanted to make sure that with this unfamiliar online mode, I don't go too fast, I go slowly. So I have a whiteboard. I'll share screen with the audience and you'll be able to see the whiteboard as I write, I hope. I also hope that if there are any questions or doubts, etc., or clarifications which you want to make in between, please don't hesitate to stop and interrupt the talk so that we can dispose it off. There is no particular portion to be covered or anything like that. I just want to have a kind of chat about the subject of statistical mechanics today in the 2 lectures. So since we are not compelled by to cover a fixed amount of material, I hope you'll be able to have a friendly discussion of some of the foundations of this subject. So let me start by sharing screen, and I need a little bit of help on that. Let me first get the whiteboard here already. I will also mute my video because of the bandwidth problem so that you can see the screen and you won't be able to see me during the talk. So if that's all right with you, let's get started. mute this, and then I will share screen. You have to let me know whether you can see the whiteboard. Somebody has to let me know whether you can see the whiteboard.
Yes, sir. Yes, sir. We are able to see your screen, sir.
All right. So here we are. We are going to speak about the subject of statistical mechanics. I'm laboring under two handicaps here. The first is that this tablet is too big to fit on this table, so I've kept it on a slight different surface on a stool next to me. The second point is that, again, it's not like writing on a blackboard. It tends to slip. So my already shaky handwriting might become a little shakier. Please pardon me for that. Now, the subject of statistical mechanics, broadly speaking, can be broken up into two pieces. One is the statistical mechanics of systems in equilibrium, and the other is the statistical mechanics of systems which are not in thermal equilibrium. So that goes under non-equilibrium. And that is an ongoing subject. Equilibrium statistical mechanics, we pretty much understand, largely the creation of people like Boltzmann, Gibbs, and Maxwell in the 19th century. But a huge amount of development has taken place since then, of course, by a large number of contributors. On the other hand, this subject, non-equilibrium statistical mechanics, is still an ongoing endeavor. But there is some basic facts known about it, in particular close to thermal equilibrium, which I will define carefully. What happens to systems which are taken a little bit away from thermal equilibrium and left alone? How do they come back to equilibrium? That part is understood fairly well and goes under the name of linear response theory. But the general, very far from equilibrium problems are difficult, and they are in fact the topic of current research. The foundations of equilibrium statistical mechanics are also the subject of current research, because there are tricky points here about the generality with which the subject applies to various cases. In particular, in astrophysics, for instance, where you have clouds of gases, interstellar gases, with gravitation as the main force, many tricky things happen since the normal thermodynamic limit doesn't work in that case, and so on. So we keep that in mind. And today in the morning, we will talk about equilibrium statistical mechanics. And in the afternoon, we'll come to the basics of non-equilibrium statistical mechanics. Now, this equilibrium statistical mechanics, as the name suggests, deals with subjects in thermal equilibrium. We need an operational definition of thermal equilibrium. And let me give you the example of a gas of particles, say an ideal gas, for instance, although that's not important, in a container. Now, the particles in this container, the molecules are undergoing collisions with each other, and certainly the dynamical variables, their positions, their momenta, and so on, they change with time. On the other hand, under suitable conditions, the system as a whole is in thermal equilibrium, meaning that macroscopic quantities or average quantities of macroscopic variables, such as the pressure, the average force on the walls of the container per unit area, for instance, the temperature, and so on, they remain constant in time. The mean density, for instance, remains constant in time. So we will take as an initial operational definition of thermal equilibrium the statement that the macroscopic, the averages, the statistical averages of large quantities, the macroscopic quantities of variables, remain constant in time. This also means when you take an average, you have to specify the distribution or probability distribution over which you take the average. That average, that probability distribution, remains constant in time. It's called the equilibrium distribution. As we all know from basic physics, in a gas, for instance, an ideal gas at some fixed temperature, classical ideal gas, the distribution of the velocities or momenta of the particles is according to the Maxwellian distribution of velocities. that is not time dependent. It's a time independent macroscopic distribution, velocity distribution. And in the afternoon, we will talk about a time dependent variable, time dependent version of the Maxwell distribution, which tends to the Maxwell distribution as equilibrium is reached. So we start with equilibrium statistical mechanics, and the way we'll do this is to go get a page. We'll assume that we have a large system, very schematically, that is my system, and it contains, it's in isolation. We will assume that it's in thermal isolation, which means that the total energy of the system, let me call it E total, is given to you with some finite resolution delta E, it's constant in time. And just to be specific, let's suppose that the volume of this container is V total and the number of particles in it is N total. Now, classically, and we'll start with the classical case first. Classically, there are individual particles in it which are undergoing perhaps some interaction with each other, contained in this isolated system. It is isolated from the rest of the universe. We start with that assumption, so that no particles are exchanged with the rest of the universe, no matter and no energy are exchanged with the rest of the universe, maintaining the energy at some constant value, the total energy of the system at some constant value. How is it described classically? Well, you would describe the variables as the various Q's and P's, the various generalized coordinates and the generalized momenta, and there would be as many of them as there are independent degrees of freedom. And in phase space, one should imagine some shell of some kind, schematically like this, such that E is equal to constant. This is the energy hypersurface in phase space, in the space of the Q's and P's of the system here. And then if you start with a set of initial conditions denoted by this little volume element in phase space, as time goes on, this volume element will get distorted and move around in this phase space, etc. The assumption is that given enough time, which is not really much time needed at all, this little element or portions of this little volume element will spread over uniformly and mix in this entire phase space, such that any representative point visits any given neighborhood in phase space equally frequently and spends an equal fraction of time in that volume element. This is the postulate of equal a priori probabilities. It says that the number of microstates of the system is enormously large, and let me denote that by omega total. A microstate is a specification of the volume element in phase space, but then the number of volume points is infinite, so we need to introduce quantum mechanics here, or at least quantization idea, and the volume element is D 3n Q D 3n P, 3n being the total number of particles, the total number of degrees of freedom. So there are 3n of these Q's and 3n of these P's. That's a volume element in phase space divided by Planck's constant to the power 3n, because we know at the bottom of our hearts that nature is quantum mechanical, classical physics is an approximation, and that cells in phase space cannot be resolved with finer resolution than is possible given the finiteness of Planck's constant. So this is to make sure that you can count the number of cells in a continuous medium. And that's always put in here. It can be made rigorously justified. It's rigorously justified once you go to quantum physics, but right now we're not interested in doing it in a quantum mechanical, fully quantum mechanical language. So the postulate of equal a priori probability says that any such cell is as probable as any other cell for the representative point to reside in at any time. Therefore, the probability of any one, the system being in any one of these cells, is 1 divided by the total number of such cells, which is omega total here. Now, what does that imply? That implies immediately a large number of connections. And this very simple postulate apparently simple postulate, and I'll repeat it again, the fundamental postulate of statistical mechanics. Let me get this cursor going. Says that the probability of being in any one cell or being in any microstate is 1 over the total number of cells, immediately implies the following consequence. Here is my large big system here, isolated system, parameterized by the total energy, the total volume, and the total number. But now let's make an imaginary experiment. Let me say that the system is divided into two, partitioned into two quite arbitrarily, into a system A and a system B. Now, A and B are transparent to each other in the sense that particles will move from A to B and B to A. So this is a partition only in a fiducial partition, not a real one. And then what happens? Well, if I say that A has got at any instant of time energy E, volume V, and number of particles N. Similarly, this has B has E prime, V prime, and N. And the system is in overall thermal equilibrium with particles and energy being exchanged between these two partitions all the time. In thermal equilibrium, I would expect the following to happen. I would expect that most of the energy of the system, E total, resides in E prime and in E, either in A or B. In other words, the assumption is that the system is so large that the number of degrees of freedom at the partition responsible for the interaction between A and B is small compared to the number of degrees of freedom of either A or B individually. Once I make that assumption, I could write the following. I could ask the following question. What is the probability P subscript A that the system A at any given instant of time has an energy E? I should also include V and N, but for the moment, let me skip that. It's assumed that they're already present just for algebraic simplicity. What is this equal to? By the postulate of equal a priori probabilities, it means it's equal to 1 over the total, sigma total of E total. That's the total number of microstates of the system, accessible microstates of the system at energy E total, multiplied by the number of microstates of the full system such that the energy of A is E and the energy of B is E total minus E prime. Therefore, since these two systems here are large and the number of interacting degrees of freedom is small, you can assume, with a very good approximation, that the number of microstates of the full system such that the subsystem A has energy E is simply a product of the number of microstates of A, omega A, corresponding to energy E, multiplied by the number of subsystem microstates of B corresponding to energy E prime, which is equal to E total minus E. So there's a very subtle assumption here that the number of degrees of freedom of A and B are so large that the number of degrees of freedom in the partition is negligible compared to the individual number of degrees of freedom. And therefore, this probability, omega total, such that energy of A is E, factors into these individual products of individual factors of the number of microstates of A and B respectively. Now, these are enormous numbers, and let's see what they could look like. Well, from our experience with gases, we know, for instance, that the number of microstates is likely to increase for a given energy E, is going to increase like some enormous power of this E. It's going to go like E to the power of number of degrees of freedom or something like that. So this omega A has a curve which increases with E in this fashion. If this was E and I plot omega AE, it looks like it's a rapidly increasing function of E. On the other hand, for a fixed E total, omega B, as E increases, the argument of this number of microstates decreases, and therefore it starts at some finite value and sharply goes to zero as E increases towards E total. The product of these two functions, one of which is rapidly decreasing and the one is rapidly increasing, is some kind of very sharp bell-shaped curve in between. And as the numbers increase towards Avogadro's number and beyond, this peak becomes sharper and sharper and the distribution becomes thinner and thinner. So PA of E is practically like a delta function at some intermediate value of E, of the energy E. Now, what does that mean for us in practice? Well, it implies that you should really do these calculations because they are very large numbers. You should do these calculations not by taking P of E, but by taking the logarithm of PA of E. And asking what this is. This is logarithm omega A of E plus the logarithm of omega B of E total minus E plus or minus in this case because it's in the denominator minus a constant because we have kept our system isolated in thermal equilibrium. So the total number of particles, energy, volume, etc. remains constant. That's just a constant there. Now, the log of a function, log x, is a monotonically increasing function with x as x increases over positive values. The log increases monotonically. So whether we take a maximum, we try to find the maximum of either P A of E or the log of PA of E, doesn't matter. And in thermal equilibrium, you would expect that delta over delta E log PA of E should be equal to 0. So it should be at an extremum. But what does that imply here? Well, it's equal, this implies that delta over delta E, well, let's write it in the same line, equal to delta over delta E log omega A of E. And then the derivative of this with respect to E, which as you can see produces a minus sign immediately because this is E total minus E. So you have to differentiate that with respect to E. That gives you a minus 1. So this immediately gives you next minus delta over delta E log omega B. For the moment, let me write it as E prime here. And the rest are constants. So this in turn implies that delta over delta E log omega A of E is equal to, if you move this to the right hand side, the 0 on the left here, you get delta over delta E log this quantity here. So it immediately implies that delta over delta E prime, let me write it in this form itself, log omega B of E prime. With the understanding that E prime is E total minus E. So this belongs to subsystem B, this belongs to subsystem A, and it's saying that there is some equality between a certain quantity calculated for A and the corresponding quantity calculated for B. Now that's a really weird thing because, sorry, I should have said plus here. Plus here. So when you move to the right hand side, it will be a minus, but E prime is E total minus E, and therefore that minus goes away and you get delta E prime here correctly. Now you can recognize what this actually is. Remember the Boltzmann formula, we make an immediate connection with thermodynamics, although this took a long time to happen historically. Boltzmann had this famous formula, S is K Boltzmann, I'll just write it as K for simplicity, log omega. The famous Boltzmann formula for the entropy in the microcanonical ensemble. This is engraved in Boltzmann's tombstone in Vienna. SSK log omega. There's a wrong historical romantic story about this tombstone in Vienna, which I will not get into here, maybe later. But if you put that in, it's really saying that the entropy of A is equal to the entropy of B in some sense. But then the derivative with respect to energy of this entropy. And what does that tell us? What is actually happening? And what's the dimensionality of these quantities? Well, let me cut a long story short and say that omega itself is dimensionless. The log of this quantity is dimensionless. There's an E in the denominator. So the whole thing has dimensions of 1 over energy. And this implies, in fact, that beta of A is equal to beta of B. Beta is 1 over KT, 1 over the inverse temperature. That's really what is happening. You multiply both sides by Boltzmann's constant, then it's really saying the derivative of the entropy with respect to the energy is the same on both sides. Yes, please. So let me make that more convincing. We'll go back now and assume that we know a little bit of thermodynamics, because that's where the connection comes from. Remember what thermodynamics says. The first two laws of thermodynamics combined together essentially say that TdS is the internal energy, but let me call it as E here, because we are working in the microcanonical ensemble. The internal energy is the statistical average energy, statistical average of the energy. However, in the microcanonical ensemble, we've seen that the distribution of the energy is really, really very, very sharply peaked. Therefore, the fluctuations about the mean are negligible, and thermodynamics applies, and therefore TdS is dE. This is a little unconventional notation. We should really write du. We'll do that when we come to the canonical ensemble. Plus PdV for a fluid system. And if the number can also change, then there is a minus chemical potential times the number of particles dN. Therefore, it says ds is 1 over T dE plus P over T dV minus mu over T dN. But ds now, it says, is a function of the independent variables E, V, and N. So this is also equal to delta S over delta E, keeping T and N constant, V and N constant, sorry. Times dE plus delta S over delta V, keeping E and N constant, dV plus delta S over delta N, keeping E and V constant, dN. And it says now what condition said that delta S over delta E was the same on both sides. But you can see what this is. This quantity is nothing but 1 over the temperature. This quantity is nothing but P over T. And this quantity is nothing but minus mu over T. So in the microcanonical ensemble, we have derived now this very important relationship, which says the temperature of A must be equal to the temperature of B, which is exactly what you'd expect on physical grounds. We've derived this now. We've derived the fact that whatever this temperature is, it's a measure of average energy of random molecular motion. It must be the same on the two sides of this partition here, which is what you would expect on physical grounds. So A and B have the same temperature. In exactly the same way, instead of E, I could have chosen V as the independent variable, and I would have discovered that delta log omega A over delta V is equal to delta log omega B over delta V prime, which would have implied that the pressure in the part A is the pressure in the part B, and similarly with N, the chemical potential of A is the chemical potential of B. So it says that the derivation from the fundamental postulate of statistical mechanics in the microcanonical ensemble for a system in thermal equilibrium, an isolated system at thermal equilibrium, says that if different parts of the system are at the same temperature, they are at the same pressure, and they are at the same chemical potential. Now, this chemical potential is a concept that causes a great deal of confusion in people's minds, what exactly it is. It is, roughly speaking, the following. As we know, it's the Gibbs energy per particle, and we know what the Gibbs free energy is in thermodynamics. But let me say it in sort of physical terms. What the chemical potential of a system is the following. If you have a statistical collection of particles, the energy under certain external conditions, maybe constant temperature, constant pressure, whatever conditions you prescribe, the chemical potential under those conditions is the cost in energy to add one more particle to that statistical ensemble, keeping those conditions fixed. So this is the reason why when water is boiling in a container in the open atmosphere, the chemical potential in the vapor phase is exactly the same as the chemical potential. The Gibbs free energy per particle is exactly the same in the vapor phase as it is in the liquid phase. It costs just as much energy to put the molecule, extra molecule in the water phase as in the vapor phase. And that's why they are in thermal equilibrium and you are in a state where the two phases coexist. So on the coexistence curve, chemical potentials of the two different phases are equal. Here it's a simpler situation. It's saying that if you've got a single system, the chemical potentials on the two sides are exactly the same. It doesn't matter, it's going to cost you the same energy to put up one more particle in A as in the subsystem B. So this is the physical consequence of the microcanonical ensemble which has emerged, which is nice for us. Now we can make connection with the thermodynamics in several different ways. And let me just point out one thing, and that is I wrote this law as ds is equal to, on this side, dE divided by T plus P over T dV minus mu over T dN. This is sometimes called the entropy ensemble because it treats S as a function of E, V, and N. But you could equally well have chosen the energy ensemble and written this thing as dE is equal to TdS minus PdV plus mu dN. For a simple system, one component system, this is the corresponding equation. And then you can derive, you can treat the energy as the corresponding thermodynamic potential in the microcanonical ensemble, just as you treat the Helmholtz free energy. So you have E is equal to E of S, V, and N. If you want to make a Legendre transform and go to the Helmholtz potential, then F is U minus Ts or E minus Ts in this case, and this becomes T, V, and N. If you want to make one more Legendre transform and go to the Gibbs potential, that is a function of P. I should really write it properly. Function of T, P, and N. And you could also go to the enthalpy, which is a function of S, P, and N. It's clear you have 8 possible potentials with 3 different independent thermodynamic variables, but not all of them are non-trivial. For instance, you could not go to an ensemble. You could also do Legendre transforms and change. You could, instead of regarding S as the independent variable, you could regard T as the independent variable. Similarly here, instead of regarding V as the independent variable, regard it as P, and here mu rather than N. But then you cannot have a potential, a thermodynamic potential, which is a function of T alone, P alone, and mu. This is not possible because all these 3 quantities are intensive quantities like densities and not extensive quantities. So there's no information on how big the system is, how many particles there are, what the volume is, what's the size of the system. Therefore, this thermodynamic potential, if you calculate by doing a Legendre transform on this equation here, I urge students to try this out, you will discover that this quantity is identically 0. Not possible at all. In fact, there are 6 thermodynamic potentials. 4 of them are very commonly used here. There are a couple more which are not so commonly used. So this takes us now into statistical mechanics of in the microcanonical ensemble, but it's not very useful for the following reason. We've started with a system in isolated in thermal equilibrium, which is isolated from the rest of the universe, but that's not what happens at all in practice. Every system is connected to the rest of the universe, and what do we do about it? Well, we need to find what happens if you took your big system and put it in the middle of a much, much, much bigger system here. Call it the heat bath, for example. And this is my system. And this heat bath is exchanging energy with the system, driving fluctuations in it. For instance, when you take a vessel of water and put it on the stove, you put it in a thermal bath, and this is driving a lot of energy into the system. And the question is, what happens now? What's the meaning of thermal equilibrium? What happens now? That takes us to a more interesting problem, which is the following. And this is the so-called canonical ensemble. And now my system is like this, the huge system. Again, omega total of E total, N total, V total. My subsystem A is extremely small, A, and I've denoted it, made it small even to look at, just to remind ourselves that this is an extremely small system here. It's got some particles in it, it's got a certain volume, etc., etc. But the important thing is that the number of degrees of freedom in B is now much, much larger, astronomically larger than those in A. A could in fact be 10 molecules, and this could be Avogadro's number of molecules in B. Then it's very clear that A is subject to very large fluctuations. On the other hand, B is hardly affected by what's going on inside A. So if A gives some energy to B, you'd hardly notice it because of the large number of degrees of freedom. But if B pumps energy into A, you'd notice it immediately. And the question asked is now, what is the probability P A that the energy of A is some given number E? Just to remind ourselves that this is a small number compared to E total, I will call it epsilon. E total is equal to E prime plus epsilon now, in this case. Assuming again that the interactions are negligible, which is not a very fair assumption here and requires careful justification, but we will see what this is going to lead us to here. What is this quantity equal to here now? Now it's very obvious that the normalization constant will again be the same as before on the total of E total, because the full system is isolated. It's the subsystem A that is not isolated. Therefore, it is 1 over omega total, E total, times what on top? Well, it's the number of microstates of the full system such that the energy of A is epsilon. And that is largely governed, since the energy of A itself fluctuates rapidly, but the energy of B does not fluctuate so rapidly since E total is constant. This is largely governed by omega B of E total minus epsilon times some possible normalization constants, etc. But that's the expression for the probability that the energy of A at any instant of time is epsilon, keeping in mind the fact that this is a very rapidly fluctuating random variable. It's a random variable that fluctuates, that has large fluctuations, and the distribution PA of epsilon is nothing like the PA of E that it was in the earlier case of the microcanonical ensemble. Once again, how are we going to deal with this? We need to know everything about the heat bath, but in general, we don't know what's happening in the rest of the universe. This B is the rest of the universe, and this A is the small subsystem that you are interested in. So how are we going to take advantage of the fact that we don't know much about the heat bath itself? Well, once again, we're going to look at log functions. So log PA of epsilon is equal to log omega B of E prime. E prime is E total plus epsilon. I should write this out explicitly, so let me write this. Yeah. And we'd want to find out what this function is. Once again, as before, we use the method of most probable distributions, which means that we were looking at the peak of this function, wherever it is, and we're going to equate its derivative to 0. But before we do that, remember that we can write it in the following way. Just look at this argument here. E total is much, much larger, unimaginably larger than epsilon. Therefore, I can do a Taylor expansion of this function and write this as log omega b at the point E total plus the first order term, which is equal to minus epsilon times delta over delta E prime log omega b of E prime, where E prime is E plus E total plus epsilon, plus higher orders in epsilon, so order epsilon squared, and so on. Minus a constant. So I should put some constant here, plus some log, plus some constant, which is independent of epsilon. We don't know this. We don't know this. We don't know what's happening. We do know this. But what is this quantity here? As E total becomes much, much larger than epsilon, you can neglect terms of order epsilon squared and so on. And therefore, it says log PA of epsilon is equal to some big constant. Let me call it C once again, just to avoid confusion here. C minus epsilon times the derivative of the number of microstates of B at energy E prime with respect to E prime, evaluated at E prime equal to E total. That's the Taylor expansion. But what is that quantity? That is simply the temperature of the bath B. So this is equal to E divided by beta. Beta is equal to 1 over K Boltzmann times the temperature of the system B, of the heat bath here. That gives us what the expression for PA of E itself is. PA of epsilon is equal to some other constant, so let me call it C prime, E to the minus beta epsilon. And lo and behold, the Maxwell-Boltzmann factor has emerged out of nowhere magically. And now if I plot PA of epsilon with respect to epsilon here, this is no longer the sharply peaked curve that we had earlier in the microcanonical ensemble, but rather an exponential, decaying exponential, which goes down like this, with the peak in fact at epsilon equal to 0. This is the distribution in the canonical ensemble. And this famous factor here is the Maxwell-Boltzmann factor. This is independent of whether the system is classical or quantum mechanical. I should point this out. This distribution is called the Maxwell-Boltzmann distribution. It can be confused with the Maxwell distribution of velocities or energy of a classical ideal gas or a classical system. That's a different Maxwell-Boltzmann statistics. This is the Boltzmann factor, E to the minus beta epsilon. And it's very different from what we had earlier here. So now let's see if we can apply this. Can we do this? Can we derive, for instance, the laws of thermodynamics from it? Can we derive the law ideal gas at least? Can we do something about it? Can we say what the energy of the ideal gas is or the equation of state of an ideal gas is? Well, let's try doing that. For that, we need to introduce a concept called the partition function. And that's the thing I turn to next. In the canonical ensemble. And the definition is the following. This is Z is equal to, it's a normalization constant for, oh, I should mention that properly. Remember, we found that PA of epsilon is some constant times e to the minus beta epsilon. This constant was very difficult to find because it involved knowledge of the rest of the universe, which we don't have. But we can now use a trick to find out what this constant actually is. And that's as follows. And it's most easily illustrated in terms of pictures. If I pretend for the minute that the subsystem A, energy of A, can take on values epsilon naught, epsilon 1, epsilon 2, dot, 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 maybe all the way to epsilon infinity. So in other words, we've assumed that the levels of this energy of A are discrete, just to picture things clearly. If that is the case, this normalization constant is utterly trivial to find, because we know that the summation PA of epsilon over all possible states, energy values J, 0 to whichever way it goes, finite or infinite, this must be equal to 1. Because the system A must be in some energy state at every instant of time. So the total probability of being on any instant in energy state is 1 here. So therefore, this constant is simply 1 over this number here, whatever it is. So we have a formula which says PA of epsilon J, for instance, or epsilon, any particular energy level, PA of epsilon I, for instance, must be equal to e to the minus beta epsilon e to the minus beta epsilon I divided by summation J equal to 0 upwards e to the minus beta epsilon J. This normalization constant here is very, very crucial. It is called Z, the canonical partition function of the system. But notice the cleverness here. The cleverness is we don't know what this constant is because it looked like it depended on the rest of the universe other than the system A. But we got rid of that ignorance by saying, no, no, no. If you tell me everything about the energy levels of A, then I can tell you what that normalization constant is by writing down the partition function here and dividing, so that this equation is guaranteed to be satisfied here. Notice the cleverness here. This portion of it is a system property, epsilon J, of the subsystem A. It has nothing to do with the rest of the universe. You tell me this system and say these are the possible energy values of the system. Continuous or discrete doesn't matter. Where is the rest of the universe come in? The rest of the universe is driving fluctuations in energy into the system, and the ignorance of the rest of the universe comes in its temperature here. So the entire information about the rest of the universe, or the heat bath as it's called, is subsumed in the knowledge of its temperature. And temperature therefore can be regarded as another word for the ignorance of what's happening to the heat bath. All that the heat bath does is to drive fluctuations into the system that we are interested in, characterized by this typical number, characteristic number beta with the inverse temperature of the heat bath here. So this is where the statistics comes. The epsilon J is discovered either by classical or quantum mechanics for a given system, but it's e to the minus beta here. The beta here comes from the rest of the system. In fact, I like to say that if you had the possibility that you have more than one possible, if you have more than one possible state energy at the same energy value, so suppose this is the way your energy spectrum is, etc., with a lot of degeneracy, then it's clear that Z is equal to, over here, you must write the states of the system, states J, e to the minus beta epsilon J. But you could also write this as levels J. Now J labels the levels of the system, energy levels of the system, and you must count this as many times as there are distinct states corresponding to a given energy level. So this is equal to G J e to the minus beta epsilon J, where Gj is the degeneracy factor of level epsilon G. So that's the correct formula for the partition function here. And if you had a continuous spectrum, this summation would become an integration over epsilon. And what sort of integration would that be? Well, it would be equal to e to the minus beta epsilon, rho of epsilon, b epsilon, where this is called the density of states. People who do condensed matter physics know very well that the density of states is all there is to the whole system. And now I should be careful about the limits of integration. It runs over epsilon. And let me point out here that it cannot run to minus infinity, because if you have a system whose lowest energy level is at minus infinity, the system would collapse. It would undergo what's called collapse to the origin and be finished. So we're always going to look at physical systems whose energy is bounded from below, and let me, without loss of generality, take it to be 0, could possibly go all the way up to infinity, could in fact stay at some finite value. We don't care about it. But this is the basic quantity here in this case. And I like to say that this is what justifies the name statistical mechanics, because the statistics comes in this part, e to the minus beta epsilon, because of the ignorance implied in writing down beta. And the mechanics comes in discovering what the density of states of the system is. So statistics and mechanics make statistical mechanics. It's a nice way to remember what is going on here. Now, once you have this, all physical quantities are known in terms of it. For instance, if you ask what the total energy, average energy of the system is, it's a trivial matter to prove that the average value of the energy of the system, the average value of the Hamiltonian of the system, more technically, this is what is written as the internal energy U very often. This quantity here, this is equal to a summation over the Hamiltonian, or the energy epsilon j, e to the minus beta epsilon j, times the degeneracy factor Gj, times the states, the levels J, divided by Z, the normalization factor Z. And it's a little bit of algebra to show that this looks like you've differentiated the numerator with respect to beta to bring this epsilon j down. And indeed you have, because there's a simple formula that tells you that U can be written down in terms of the partition function as minus delta over delta beta log Z. So let's try and do that. And we know what this quantity is, minus delta over delta beta log Z, because just to jump a little bit, the Helmholtz free energy as you know is given in thermodynamics by U minus Ts. But in statistical mechanics, it is equal to minus K Boltzmann T log Z. And that's a relation not very difficult to establish. And once you know the Helmholtz free energy, you know the pressure of the system, etc. And let's try and calculate it in this case, what happens here. We'll try to calculate from first principles what this whole thing is. Well, for the classical ideal gas, it's not a very difficult calculation. Let's do thermodynamics here. This says dF is du minus TdS minus SDT. But du in its turn is TdS minus PdV, keeping the number of particles fixed for the moment. We don't write the mu dn term here. Du is TdS minus PdV minus TdS minus SDT. And this TdS cancels against that and gives you minus SDT minus PdV. This implies that the pressure of the system, P, if you compare with these two things, the pressure of the system here is the derivative of F with respect to the volume with a minus sign. So minus delta F over delta volume, keeping the other variables constant, in this case T and N constant. So we need the derivative of the free energy, Helmholtz free energy, with respect to the volume keeping the other quantities constant. So P is minus delta over delta V F, keeping T and N constant. How do we do this? How do we write this partition function? Well, if you have a classical ideal gas, now we have specified our system in some container, and it's got temperature T, volume V, number of particles N. Then we need to calculate what the partition function is. If it's an ideal gas, the only interaction between the particles is instantaneous collisions, elastic collisions with each other. That's what causes equilibration of the system to remain in thermal equilibrium. Otherwise, there's no interaction at all. And therefore, you can write the partition function Z of the system, which remember was for the full system, it was a thing of the form G j e to the minus beta epsilon j. You can factor this sum by saying the energy Ej is really the sum of the energies of the individual particles, and therefore this in some sense is equal to little z to the power n, where little z is quote unquote the partition function of a single particle. But what's that equal to? We just have to find what the number of possible microstates is, because that's what the partition function is telling us. We want to simply compute the microstates of the system. So little z is equal to, well, first of all, there is an integration because you're going to sum over dp dq. So that gives you a volume factor because it doesn't matter where the particle is inside the system, divided by h cube because it's a single particle, times an integration over d3p, all possible momenta, e to the minus the Boltzmann factor, which is beta p squared over 2n. And we have to take this to the nth power. And we also have to make sure that the entropy is extensive quantity. That is done by taking into account the indistinguishability, underlying indistinguishability of the particles, even in classical physics, by dividing by this famous fudge factor n factorial. And for the moment, we will leave that out, and we try to compute this quantity here. This is equal to v over h cubed. Do this in Cartesian coordinates. It's minus infinity to infinity dpx e to the minus beta px squared over 2m cube, because the y and z integrations are exactly the same. And therefore, this finally gives, to cut a long story short, it gives v, apart from constant, which I'm going to ignore at this point. We write it as proportional to v times this Gaussian integral, and that's equal to square root of pi over the constant a, which is sitting here. So this becomes 2 pi k Boltzmann t to the power 3/2, because there is a cube here. And therefore, we have our final result, which says z is equal to, apart from some constants which are not relevant here, there's a v, and then there's a 2 pi mk Boltzmann t, the whole thing to the power n. This is 3/2 to the power n. And if you put in the Sacco-Tetrode fudge factor, there's a 1 over n factorial as well. And what we need to do is to take the log of this guy and carefully keep into account, take the derivative with respect to v. And you can see that all that's going to happen, if you did that, is the derivative, there's going to be an n here, so this becomes n log v when you take the logarithm. And if you take the derivative of that, you get n over v. So this is going to lead immediately, and I leave to the students to find this equation. It's going to lead immediately to the fact that the pressure of the gas multiplied by the volume, I bring it to the right-hand side, this is equal to n times k Boltzmann times t, which is the equation of the ideal gas equation of state of the particle here. So we found the equation of state of the ideal gas, and we know we are now on the right track. By the way, this is difficult to prove from first principles, actually, because it has to do with what you assume about the collisions between the particles. In fact, it's a hard problem to prove, but we won't get into that at the moment. But we know that this is from elementary considerations, the equation of state of the ideal gas. In exactly the same way, you can also find the internal energy, and that turns out to be 3/2 times Nk Boltzmann T here. It's interesting to note that the ratio of these two quantities, if we eliminate Nkt, it says PV is also equal to 2/3 of U here, which implies that the pressure of the part of the gas is 2/3 U divided by V, which can be written as 2/3 of little u, where little u is equal to U per particle, the average energy per particle. So dimensionally, you can see that the pressure is force per unit area. Little u is the energy per unit volume. Sorry, I should write this as volume. Energy per unit volume. So the pressure is 2/3 the energy density for a classical ideal gas. That is in fact the right way to remember what the equation of state is. And sometimes these numbers can actually have a lot of physical significance. Otherwise, they're just constants. But in this problem, they have a lot of significance. So I recall to you what happened here. Where did this 3 come from? Where did this 3 come from? It came from the fact that you had a triple integral to do in the momentum space, which came from the fact that you had 3 dimensions. So this statement, P is 2/3 U, this comes from this dimensionality of space-time, of space rather. Spatial dimensions. This 2 is a little more subtle, and it came from the 2 here. And this 2 really in turn came from the equipartition theorem, because it said every degree of freedom of a particle has energy half kT, and therefore 3 degrees of freedom have energy 3/2 kT. And if you have n of these particles, the energy is 3/2 nkt. So this half came from the fact that you had the equipartition theorem, which says every degree of freedom has energy half kT. But that is not quite true. What is happening is really that you have a Gaussian integral. You have to do an integral of the form e to the minus beta px squared over 2m dpx from minus infinity to infinity. And that gave you a square root of whatever it is. And that's in turn led to the fact that you have 3/2 here. So this half came really, this 2 was the source of that half. So this numerator here, the 2 comes from the fact that the relation between the energy and momentum is quadratic. It's because epsilon is p squared over 2m. It didn't come from the 1 over 2m, the 2 here. It came really from this p squared here. If this were not true, the answer would change immediately. For instance, if you had a gas of particles which didn't have a mass, but whose energy was proportional to the momentum, epsilon equal to Cp, as in the case of a photon, for instance, then the whole picture would change. You're still in 3 dimensions. So I recall to you that in black body radiation, you discover that the radiation pressure P is 1/3 the energy density U from the Stefan-Boltzmann law. And this 1 came from the fact that it's a linear relation between energy and momentum for the case of a photon, whereas it's a quadratic relation for massive particles. But you're still living in 3 dimensions in both cases, so you've got a 3 here. Of course, I'm not claiming that U is proportional to this 2 becomes 1 in the case of photons. That's not true. U is in fact proportional to T to the power 4 here because of the Stefan-Boltzmann law. And that's because photons are not only massless particles, 0 rest mass, but also have Bose-Einstein statistics to be taken care of. So that's what we'll do next. We'll talk a little bit about quantum statistics, but this is the situation here. This relation may change. This relation, equation of state of a photon gas may change, but the ratio of the 2 will not change, and it will remain at 1/3 U here. That's a marvelous thing to notice, that for an non-ideal gas, or for a quantum gas, for instance, PV would be equal to NKT times some stuff which is very complicated to calculate. Similarly, U on this side is equal to 3/2 NKT times some very complicated stuff here for massive quantum statistical particles. But the ratio of the two would remain 2/3 U here. And if it's massless, it will become 1/3 U. So that's a nice thing to notice about these situations here. Now that brings me to what quantum statistics is. I haven't really derived this relation, but I urge students here to use exactly the same technique and derive this from this canonical ensembles partition function that we've written down. The calculation of the entropy is a little trickier. I won't get into that here at this moment, but the pressure is something that you should try. What happens quantum mechanically? Quantum statistics. Well, we have to take into account the fact that elementary particles are indistinguishable. Identical particles are indistinguishable. One electron in this universe looks exactly as the same properties as any other electron in the universe here. But you may say, well, why should I bother about this indistinguishability? I keep one set of particles here and I keep one set of particles there, and they shall not mix. Is the exclusion principle still valid? Yes. That's a quantum effect. It's still valid. These two could have been in an entangled state, for instance. And then, of course, no matter how far apart the spatial separation becomes, you still have quantum correlations in the problem. Excuse me. Get some water. Sorry. So how do we take this into account? Well, if in the remote past, two of these particles, one from here and one from here, are interacted, you have no way of knowing in the future which is where. If these two particles came along like this and underwent some interaction, and then one particle moved off like that and the other moved off like this could have happened because of an interaction of this kind, conserving momentum, or it could have been because you did this. In either case, if this is particle 1 and this is particle 2, you have no way of knowing whether this is 1 or 2 or this is 1 or 2 because of these two possibilities. Therefore, indistinguishability must be taken into account. And how do we do that? Well, there's a sort of hand-waving way of doing it. This is the subject of quantum statistics, but let me show you a hand-waving way of doing it. What did we do for the classical case? We said we want to count the number of states of the system. We said, suppose the states of a particle are given by this, for the moment, some discrete set of states like this. Etc. This is particle 1, particle 2, particle 3, etc., etc. Then one possibility is to say, well, maybe particle 1 was in the ground state here, particle 2 was in this state here, and particle 3 was in this state here. And classically, you would count each one of these things, all possibilities, and that's how you got z equal to little z to the power n divided by n factorial to put in the indistinguishability factor. These are levels. And these are particle labels on this side, and these are levels. And classical counting says, in what level is particle 1, in what level is particle 2, in what level is particle 3, and so on, and adding up all possibilities or multiplying in the case of the partition function. Quantum mechanically, this system is not distinguishable from another situation where if I
Excuse me, sir.
Yes, please.
Your
Yeah.
voice is not audible, sir.
Can you hear me now?
Yes, sir.
Is it
It's
all
little
right?
bit. It's little bit breaking, sir.
It's breaking up. Let me see what I can do. Trying to maximize the volume here. Yeah, is this better? I'll speak a
Yeah.
little louder.
Yes, sir.
Okay. Is the screen visible? Is the screen visible?
Yes, sir. It is visible, sir.
Okay, good. Is my voice clear? I'll speak a little louder.
Yes, sir. It is clear now, sir.
Okay. So while classically, count states of each particle, quantum mechanically, you have to adopt a different strategy, because this system, the distribution of these particles among these energy states, such that particle 1 is in level here, 2 is in this level, 3 is in this level, that state is not distinguishable from 1, where particle 1 is in the third level here, particle 2 is in the second level, and particle 3 is in the ground state. Not distinguishable. You must count them as one possibility, and that's it. So how do we do this? Well, it's very simple. Classically, you tally upwards like this along the column wise. Quantum mechanically, you simply find out how many particles there are in a given level. So all we have to do is to look at the occupation number of each level. So count number of particles in each level. I repeat, a quick way of understanding the difference between classical and quantum statistics is classical statistics, you tally column wise. For each particle, you look at which level it's in. Quantum mechanically, to take into account indistinguishability of particles, you count row wise. You look at how many particles there are in the first row, the second row, the third row, and so on. And that's all that there is. So instead of this formula here, you could write the Z as the contribution from each level. And let me denote that by saying, let's look at some particular level of energy epsilon and ask what is the contribution to the partition function from the level epsilon. And let me denote it by this curly little z here. This is equal to, this is proportional to, or rather it's equal to, on this side, on the right hand side, you have to write down the possible number of a summation here over e to the minus beta n epsilon over the sum n, where n is the number of particles, n particles in the level epsilon. So if in the nth row, if in the row corresponding to epsilon you had n particles, the energy is e to the minus beta n epsilon for a quantum mechanical system of ideal particles which don't interact with each other. But now we know that there are two statistics. There is the Pauli exclusion principle to be taken into account for Fermi-Dirac, and there is the Bose-Einstein factor for the Bose-Einstein statistics, the no exclusion principle. So this summation runs n equal to 0 to 1 in the case of Fermi-Dirac, beta n epsilon for Fd, and it runs n equal to 0 to infinity in the thermodynamic limit, e to the minus beta n epsilon in the Bose-Einstein case. So what does that mean? It means that the partition function has two different forms altogether. Z of epsilon is equal to 1 plus e to the minus beta epsilon in the Fermi-Dirac case, and it's equal to 1 over 1 minus e to the minus beta epsilon in the Bose-Einstein case. We're not done yet. This is what the partition function contribution is. And the corresponding energy, the average energy corresponding to that level epsilon, is equal to minus delta over delta beta. This is U corresponding to the level epsilon. So let me write U of epsilon. Log Z of epsilon. And that's equal to Let's do it for this case first. You differentiate the log, you get 1 over. Then you've got to put a minus sign because you're doing a minus derivative here. Derivative of e to the minus beta epsilon is minus epsilon e to the minus beta epsilon. What happened here? Let me write it neatly. Minus 1 over 1 plus e to the minus beta epsilon times minus epsilon e to the minus beta epsilon, which is equal to epsilon divided by e to the beta epsilon plus 1. This is Fermi-Dirac. But you could also write this as equal to epsilon times the average energy corresponding to the level epsilon is epsilon multiplied by the average number of particles in the level epsilon. So it says that in the case of Fermi-Dirac statistics, n of epsilon is equal to 1 over e to the beta epsilon plus 1. Let's write this properly. 1 over e to the beta epsilon plus 1 Fermi-Dirac. Isn't this marvelous? A very simple derivation of the Fermi-Dirac factor. Precisely the factor that you see in the theory of the electron gas at absolute zero. You make an approximation to this as beta tends to infinity. But this is the Fermi-Dirac factor, and it comes directly from the fact that the summation stops at n equal to 1, which is a direct reflection of the Pauli exclusion principle here. If you did the same calculation for the Bose-Einstein case, you would get the other factor. And let's do that. So for the Bose-Einstein case, z of epsilon is equal to 1 over 1 minus e to the minus beta epsilon. This is what we found. And therefore, u of epsilon is equal to minus delta over delta beta, z of log z of epsilon. And if you work this out, just a matter of derivation here, you get epsilon divided by e to the beta epsilon minus 1, the minus sign here. This is for Bose-Einstein statistics. So once again, this implies that n of epsilon for Bose-Einstein statistics is equal to 1 over e to the beta epsilon minus 1. The all-important minus sign here. This is exactly what you get for the photon gas for a reason which I'll explain in a minute. But you see how easily the Bose-Einstein and Fermi-Dirac factors come out. And this here can diverge actually because of the minus sign in the denominator, leading to the phenomenon of possible Bose-Einstein condensation here. Now you might argue that we simply said these particles were independent of each other and didn't say what it costs in energy to put one more particle in. What happened to the chemical potential? Well, if you include the chemical potential, then you end up with the fact that n of epsilon, and that's an interesting little exercise, this is equal to 1 over e to the beta times epsilon minus mu, the chemical potential, plus or minus 1, plus Fermi-Dirac minus is for Bose-Einstein statistics. So that's the grand result that you get for the mean number in a given energy, at a given energy level, epsilon here. And then the rest of the theory of ideal Bose-Einstein and Fermi gases proceeds from here. But this emergence of these factors, the Bose-Einstein and Fermi factors, is fairly straightforward. It comes from indistinguishability and doing a row-wise tally as opposed to a column-wise tally when you're counting the number of possible states here. So I thought I'd bring this on to your attention carefully. One final remark. Why is it that for the photon gas you had just this? Remember that epsilon was h nu, and this for the photon gas, black body radiation. This went to 1 over e to the h nu over kt minus 1. That is the correct Bose factor in this case. What is the reason why mu was set equal to 0 in that case? Any guesses on that? Well, mu, the chemical potential mu, is the cost in energy to add one more particle to a statistical collection of particles. But remember that the photon has 0 rest mass. So no matter how low the energy is, you have photons of that frequency possible. Since the frequency of photons runs continuously from 0 to infinity, mu is identically equal to 0 for photons. And therefore, unlike a massive Bose gas, the photon gas has no chemical potential at all. And therefore, the Bose factor has no chemical potential sitting in it at all. It's easy to derive from the Bose factor what the Stefan-Boltzmann law is, and let's do that quickly. Notice that U will become proportional to V times an integral over the momentum d3p, which means a p squared dp sitting here in spherical polar coordinates, over e to the beta times the energy is c times p minus 1. And then you want the energy of each particle. You want the average energy, which will give you another factor Cp out here. So this whole thing is going like p cubed dp over e to the beta Cp minus 1. Apart from some other factors, there's always a v sitting there. And now change variables, put beta Cp equal to x. And you promptly get a p cubed dp, you're going to get a 1 over beta to the power 4, which will imply that u is proportional to t to the power 4. This is the Stefan-Boltzmann law. So all these laws are all interrelated to each other. They come out from simple scaling arguments and dimensional considerations and so on. They should not be regarded as derivations, independent derivations or anything like that. So when you get one result, you should try to extract as much information from it as possible. And as you can see, we've done a lot of heuristic arguments, hand-waving arguments, which can be made perfectly rigorous. But I hope I've taken you through this little excursion to show how both classical and quantum statistics emerge quite naturally once you include the phenomenon of indistinguishability, and that the foundations of statistical mechanics starts from a very simple postulate, the postulate of equal a priori probabilities for an isolated system in thermal equilibrium. And from there, all these wonderful consequences come out by pure, simple logical arguments here. If I've communicated some of that to you, and now feel satisfied. In the afternoon, I will talk about approach to equilibrium by again taking a model system of a fluid particle, set of fluid particles, and showing how the equilibrium distribution is attained if you start from some random initial conditions. So I think I'll stop here now. And if there are any questions or comments, I'll take them.
So there are a few questions in the chat box, sir.
Sure. Let me give me a minute. Let me start video so that you can see. I don't want to click anything off because if it disappears, then I won't know how to.
Professor, minimize the screen, sir.
Pardon me?
Minimize the screen, then you can able to see the zoom.
I'm trying to do that. Well, maybe I'll stop sharing the screen. Is this better?
Yes, sir. Yes, sir. Now
Okay.
you can see the chat box. Sir.
Okay, but the problem is I've stopped sharing screen, so you won't be able to see it if I write. Let me 1 second. Let me share screen again. There's an ad for Zoom here, which I'm not able to get rid of. I'm trying to minimize it. Just give me a second. Well, it minimized everything.
Now go to the Zoom
Okay.
icon, sir.
All right. So is this, am I visible?
Yes, sir. Visible, sir.
Okay. So I'm able to share screen. Yeah, please go ahead. Okay, you have to read out these questions to me because I can't even find where the chat box is in this. Can somebody read out the questions? Or
Yes, sir.
Yeah, thank you.
Sir, the fact that CEM is limiting case of QM is known to us later. Energy is continuous in classical mechanics, but discrete in quantum mechanics, but the Boltzmann factor is common in both. Why? In classical mechanics, phase space is continuous, then why we are dividing phase space cells of finite volume, discrete picture?
Very good question. If you say that a particle, that in classical mechanics, the state of a system, a Hamiltonian system, is specified by a point in phase space, the number of points in a continuum is infinite. So right there, you are finished. But then if you ask, what's the probability of being precisely at any given point in a continuum? The answer is 0, because the number of the set of points is uncountably infinite. So once again, you seem to run into a paradox. But we know that what rescues us is the fact that Planck's constant is non-zero, and there's a finite resolution to phase space. We know that, quote unquote, really physics is, I mean, the universe is quantum mechanical. So that phase space factor, the h cube factor or whatever h to the 3n factor is put in a semi-classical way in order to correct for this and to make counting possible at all. It's possible to do the whole thing much more rigorously without bringing in this h, but still you have the same difficulty left over, namely, how exactly do you specify the state of a system in classical mechanics? Because if you're going to specify it in terms of points in phase space, then it becomes an uncountable infinity, and the measure of any given point is actually 0. So you end up with singular limits and so on. Can be handled very carefully, but at this level, we know that the physical fact that the Planck's constant is not 0 is going to come to our aid and do this. Nowhere else is it used anywhere at all. I mean, once you start taking derivatives and so on, this constant factor goes away. It doesn't get, it doesn't appear in the formulas anywhere in this case. So that's a partial answer to this question. Really, of course, we know that if the universe is quantum mechanical, you have to take classical mechanics as a limiting case of quantum physics. You have to do the exact quantum physics statistics and then come to this limiting case carefully. So is that a partial answer? Does that answer, or is there anything else that I should say?
So there is another question.
Yeah.
Thank you so much for bringing the essence of SM in few slides with fine points got clear. Can you please elaborate the meaning of zero chemical potential for photons?
Well, I sort of said in a hand-waving way that the chemical potential, which is actually the Gibbs free energy of the part of the system per particle, G over N, is the cost in energy it takes to put one more particle in an ensemble at some given temperature and pressure. That's why it's the Gibbs free energy. What is the actual statistical cost in energy? Now, this depends on how much energy is needed to produce such a particle. And the statement I made was that since a photon has 0 rest mass, the energy is linearly proportional to the momentum of the particle. And you can produce photons of arbitrarily low energy continuously from 0 upwards. And therefore, the cost in energy to add one more photon of a suitably small energy is actually 0. Can be made to tend to 0, and that's why the chemical potential remains 0. Now, as to whether the photons can interact with each other or not, and so on, there's a little subtlety here. If you take a gas of massive particles, such as a gas in a container, for instance, and you start with injecting into it the set of particles which are not in the Maxwellian distribution of velocities, then by collision with the walls of the container and collision among themselves, the particles will very quickly equilibrate. On the other hand, if you took a photon gas and you say, for instance, in a laser cavity, you have radiation there going back and forth, bouncing between the walls of the mirrors, that is not in thermal equilibrium. And the system, the reason it's not in thermal equilibrium is because there is no collisions between the photons directly at all. So the only equilibration in a black body cavity comes by the photon striking the walls of the cavity, being absorbed by the atoms in the walls of the cavity and being re-emitted. So it is in fact interaction with the walls of a black body cavity that keeps black body radiation in thermal equilibrium, not direct photon-photon interactions at all. There's one more wrinkle to it. You can ask, is that always true? Is there no interaction between photons at all? Can they not scatter each other? Well, there is a scattering process in quantum electrodynamics called Delbruck scattering, whose lowest order Feynman diagram is actually fourth order in the electric charge. That diagram, that process, which is called Delbruck scattering, does lead to a direct photon interaction at higher orders in quantum electrodynamics. But the cross section for this interaction is very small. Typically, particle cross sections in scattering theory are measured in barns, which is 10 to the minus 24 square centimeters. And this scattering process for Delbruck scattering is like a nanobarn, 10 to the minus 33 square centimeters or so in scattering cross section. So it's completely negligible at the normal intensities for black body radiation. Very intense radiation fields, of course, can lead to a measurable Delbruck scattering effect, but not under ordinary circumstances.
The next question is, how do we understand the wavelength of photons?
Pardon me, how do we understand?
The thermal wavelength of photons.
What's meant by the thermal wavelength of a photon? I didn't understand what's meant by the thermal wavelength of a photon in particular.
Okay, sir, I'll move on to the next question.
A photon has a wavelength and that's it. I mean, so where is the question of a thermal wavelength for a photon?
Okay, so the next
You see,
question.
okay. Oh, yes. If you have a set of massive particles, then you can define a thermal wavelength by saying that the energy is P squared over 2m, the kinetic energy, on the average, for instance. And if you write the de Broglie relation, lambda is h over p, and you take this p to be the root mean square momentum at some given temperature, then you end up with what's called a thermal wavelength. But that argument goes out the window once n is 0, so it's not possible. It doesn't work that way at all.
Okay, sir. And the next question is, what is the physical meaning of chemical potential MU?
That's what I said. It's the Gibbs free energy per particle. And the simple way to understand it is to ask, you have a statistical collection of particles at some given temperature and pressure. How much energy is it going to cost to put one more of those particles into the system? Yeah. So that's really what the chemical potential is.
Okay, sir. Thank you.
There's you can see in thermodynamics, it's also the conjugate variable to the number of particles. The conjugate thermodynamics comes with two sets of variables. They're called the state variables and field variables. The state variables are extensive variables depending on the system size. The field variables are intensive variables like the density of a system, for example, or the pressure or the temperature and so on. Does not depend on the system size. If you took an ideal gas of n particles in a volume V, you double the number of particles and double the volume of the gas and kept the temperature constant, then the pressure would also proportionately remain unchanged in this case. So it's an intensive quantity. On the other hand, the volume has doubled, the number of particles has doubled, etc. But when you write down any thermodynamic potentials differential in thermodynamics, you discover it's always of the form some forces times the derivatives of some fluxes. And the forces are your intensive variables, the fluxes are your extensive variables. So it's of the form f dx. Now, the chemical potential itself is an intrinsic property. It's an intensive variable, not dependent on the actual V and N of the system, but it's a function of the pressure and the temperature of the system, as the Gibbs-Duhem relation shows. On the other hand, the number is an extensive variable. The number of particles is an extensive variable. So it always comes in pairs, in thermodynamically conjugate pairs. Just like in classical mechanics, the P's and Q's come in conjugate pairs. In thermodynamics too, the field variables and the state variables come in conjugate pairs. One of them intensive, the other one extensive. And that's how all differentials are written down.
Thank you very much, sir. It's time for next session. I invite Dr. S. Kumaresan, Assistant Professor, to introduce our speaker.
Thank you.
Am I audible?
Yes,
Am I
sir.
audible? Good morning to all. I feel honored and privileged to introduce Professor V. Ramakrishnan, today's session 2 resource person, who is from School of Physics, Madurai Kamaraj University, Madurai. And he is the former director, Indian Institute of Science, Education and Research, Trivandrum. So he is a professor with the excellent academic record and proven leadership and administrative capabilities. If I go through his CV, it would be another one more session. So due to time factor, I reduce something and highlight few of his achievements. Sir, forgive me, it's not intentionally. Due to time factor, I highlight only few achievements. So about his administrative recognitions, his program coordinator, DST FIST program 2003-2006, Deputy Director, UGC UPE program 2012-2013, and Deputy Director, DST Policy program 2012. And he was the member of Senate 2006 to 2014, Academic Council member 2006 to 2014, and Advisory Committee, Academic Staff College 2006-2008, and University nominee for different Academic Council of Board of Studies Award Committee for various affiliated colleges. That is about his international fellowship. Commonwealth Academic Fellow, University of Bristol, UK 2007 and 2008. SPBL Researcher, University of Electro Communication, Tokyo, Japan 2008. Regarding his international visit for collaborative research, he has visited many countries, especially shuttling between the India and the UK, Japan, Singapore, especially few university, National University of Singapore, November 2014, Nara Institute of Science and Technology, Japan, November 2014, National University of Ireland, June 2016, University of Bristol, UK 2016, and it is a few more countries he has visited. About his achievements, especially awards and honors, International Award Fellow, Institute of Physics, London, UK since 2014, member American Physical Society 1990-1993, National Award BSR Faculty Fellowship UGC New Delhi since 2019, Junior Research Fellowship UGC New Delhi 1983, Life Member Indian Laser Association since 2009. And about his research and contributions, research paper publications. So far, he has published 170 research publications in peer-reviewed journals, research paper and presentation, national level and international level, 125, and research projects completed. Nearly 27 projects he has completed. About his grants received in lakhs, principal investigator for 200 lakhs and deputy program coordinator for 3,125 lakhs. That is research guidance. So far, he has guided PhD students awarded under his able guidance, 22 students, MPhil students awarded 27. So he is such an eminent professor with excellent academic record and proven leadership quality and also different administrative capability. So with this small introduction, I invite you, Professor, please, session is yours.
Okay, thanks, Dr. Kumaresan and Ravichandran. So good morning to all of you. My dear students, today I am just, yesterday I spoke about Raman spectroscopy. Today, my talk will be on the electronic spectroscopy. I will just narrate. So the spectral studies on molecular interactions in solvent mixtures. So you have a solvent mixture. So in this, you will have a intramolecular and intermolecular interactions. Both will predominate. So how you try to understand the inter and intramolecular interactions through various spectroscopic techniques. In this talk, I'll be just focusing on electronic spectroscopic technique. Yesterday, we have seen spectroscopy is nothing but a branch of study to study the interaction between the electromagnetic radiation and matter. The ultimate aim is to reduce the atomic and molecular structure. So a molecule will have three types of prominently three types of energies: rotational, vibrational, and energy. Each electronic state comprises of several vibration states, and several vibration states each vibration state consists of several rotational states. So the small amount of energy is required for a rotational transition and slightly larger for vibrational transition. And in terms of electron volts, you need for an electronic transitions. So yesterday we have seen about the vibrational spectroscopy. That is one of the energy level transition takes place in a molecule. So electronic spectroscopy, that is what generally people may call as an optical spectroscopy. That is transitions occurring in the valence band, or you can say the outermost electrons which are getting excited. So electronic spectroscopy is a good probe to study or to investigate, to understand the electronic transitions in an atom or in a molecule. So there are two techniques. One is optical absorption spectroscopy. Another is the fluorescence spectroscopy. These are the two techniques. That is, one is absorption process, another is an emission process. So these two techniques can be employed to understand the electronic transition. So you can see a series of cuvettes and varying colors from blue to yellow or orange. That is a same organic compound dissolved in solvents of different polarity. And you can see that in a different environment or in a different dielectric medium, the emission profile has changed. That is, you can see that it goes from blue to yellow. That means the absorption changes. So you can see the change in position, intensity with respect to the polarity of the solvent. Change in color, that is a change in the wavelength position, and you can find the change in the intensity and also the shape, the line shape will also change depending upon the polarity of the solvents. Or in principle, what we try to understand how the environment changes the band's position and the band intensity and the shape. Optical absorption spectroscopy is nothing but the promotion of an electron, that is from the ground electronic state to an excited electronic state. So this study can be understood or can be used by the solid-solvent interaction. That is, from the position, intensity, and shape of the absorption band, you can try to understand the solid-solvent interaction. So you have various orbitals. One has 2p, 3d, 4f orbitals. 2s orbital is spherical, and p is a pi orbital. It's a dumbbell shape, and so on. So you can have a sigma bond where SS orbitals got overlapped, they just merged, and sigma pp bond, that is pi bonds, pi orbitals got overlapped, or I can say that it's merged. Whereas in pi, it's a lateral overlapping of the p orbital, whereas it's a complete merging, and it's a complete merging. And this here is a lateral, the pi bond is a lateral overlapping of the orbitals. A simple case in which you have CH2O, you have a carbonyl group, it's a double bond that you might have seen. One of the bond is sigma bond, that is a merging, it's a perfect mapping of the two orbitals. Another bond is the pi bond, that is obtained by the lateral overlapping of the orbitals. And this oxygen has two non-bonding orbitals, electrons, two non-bonding electrons. So now, what are the energy transitions which can take place? So people may be knowing HOMO, LUMO. Highest molecular orbital, highest molecular orbital, and lowest unoccupied molecular orbital, that is LUMO. HOMO, LUMO, that is, people may be working the density functional theory or Gaussian. They say that the separation between the HOMO and LUMO is some electron volts. Like that, they reduce from the software. But here, it's a ground state, sigma bond. You have a pair of electrons, pi bond, pi is a pair of electrons, non-bonding electron, that's a pair. Now I can excite an electron from the sigma bond to sigma star, sigma to sigma star. So the sigma electron is excited to its first electronic state. So now you have a non-bonding electron is excited. This non-bonding electron is excited to a sigma star, and pi electron is excited to a pi star, and a non-bonding electron is excited to a pi star. So sigma to sigma star, n to sigma star, pi to pi star, and n to pi star transition. So there are several types of electronic transitions. So it all depends upon the electrons involved, that is the sigma electrons or the pi electrons or the non-bonding electrons. So in addition to that, you have a charge transfer transition, the transfer of an electron from a donor molecule to an orbital associated with an acceptor molecule. So you can classify solvents into polar solvent and non-polar solvents. Polar solvents we just might have studied from your schools. I have a permanent dipole moment, non-polar as a negligible dipole moment. So the solvents which come across methanol, ethanol, isopropanol, acetonitrile, dimethyl formamide, the protic solvents are the solvents which have hydroxyl group. An example is methanol, ethanol, like that. Aprotic solvents, they have permanent dipole moment, but does not contain hydroxyl group, that is acetonitrile. Then there is a non-polar solvent, have a negligible dipole moment. Example is benzene or your carbon tetrachloride. Of course, if people have studied molecular spectroscopy, the microspectroscopy, the people say that they are your CCl4 or CH4, they have a spherical top molecules like that. So we have a small, it's all dielectric constants, which I mentioned.
Excuse me, sir.
Yes,
Your PPT is not visible, sir.
not visible. Not at all, right from the beginning. Hello?
Yes, sir. Yes, sir.
Now? Now?
We are able to see your folder only, sir.
Oh. I will come back again. 5. See. Select a window, I could not see.
So just to click the share screen button, sir.
Yeah, I'm just. Now you are able to see. Hello.
Yes, sir.
Yes,
Yes,
sir.
sir.
Now.
Yes, sir.
Now.
Yes, sir.
Yes, sir. Not in slideshow mode, sir.
Okay. Now.
Yes, sir. Now in mode.
Now
Slideshow.
this all you have not seen earlier.
No, sir. We didn't see, sir.
Pardon?
We didn't see, sir.
Okay, so I can see the series of cuvettes where in which color starts from blue to orange. So the same organic solvent dissolved in different polar solvents. So there's a change in the wavelengths. And of course, if you record the spectrum, you can see the intensity and also the shape. So optical absorption spectroscopy is nothing but the promotion of an electron from a ground electronic state to an excited electronic state. So this is what I have told you: HOMO-LUMO, highest occupied molecular orbital, lowest unoccupied molecular orbital. So here you have C to sigma to sigma star transition, N to sigma star transitions, pi to pi star transitions, N to pi star transitions. So in addition to that, you may have the charge transfer of an electron from a donor molecule to an orbital associated with the acceptor molecule. So these are all things you can see now. Hello?
Yes, sir. Yes, sir.
So polar solvents, that's all I explained. So you have various solvents with a different dielectric constant. So it's a simple this thing I can tell you. So it is a 1,5-diaminoanthraquinone. So you can see that optical absorption is taken. It's basically you see the Beer-Lambert's law. So you have the absorbance, but that's the percentage is not given, but it's maybe the taken and it's missed. Sorry that. So you have it goes from 400 to 550 nanometer. And it's taken and CCl4. So you can see that there is a dual character. And a methanol is a polar protic solvent, so it has shifted. And here propanol. So propanol and methanol, it has the same structure. That is something like this. When it's the DMF dimethyl formamide, CHCl3. So dimethyl formamide also, it has the slightly dual emission, and CH3Cl, CHCl3, the dual emission is almost 0. So the peaks are redshifted. The peaks are redshifted in polar solvents. That is with respect to here. Here is a polar solvent. These are all redshifted. It is greater in polar protic solvents. It's greater in propanol and methanol compared to your CHCl3 and DMF. It is weakly structured in nonpolar. That is what I said, a dual emission. It is weakly structured in nonpolar and polar protic solvents. It has completely disappeared in polar protic solvents. So the same material, same fluorophore, or the same dye dissolved in solvents of different polarity. When you take the optical absorption measurements, it shows a weakly structure in a nonpolar solvent, and it undergoes a redshift in the polar solvents. but the shift is greater in polar protic solvent. There, a polar solvent which has a hydroxyl group, and it is less lead shifted in a polar solvent which does not have a hydroxyl group. So that it is called the solvatochromism. That is, depending upon the solvation shell or the polarity of the solvent, the emission profile or the absorption profile has changed. So that is called solvatochromism. It is a positive solvatochromism. On increase in solvent polarity, transition energy shifts to a lower energy. That is a bathochromic shift. And a negative solvatochromism, on increase in solvent polarity, transition energy shifts to higher energy. That is when it shows the red shift as a blue shift. So the blue shift is a hypersochromic shift, and the red shift we have a bathochromic shift. So earlier we have seen optical absorption, fluorescence spectroscopy. It is an emission of photon from an electronically excited state. So you have absorption. It goes from the ground electronic state and it goes to the various excited electronic states. Now it goes to the S2 state. Then it makes an internal conversion. That is a non-radiative transition between two electronic states on the same spin multiplicity. Then it makes a vibrational relaxation. That is between the vibration levels in the excited electronic states. Then it makes the emission. So you have the emission from S1 to S0. So this is absorption and this is emission. So the fluorescence is a Stokes shifted one. It has a, energy released in the low frequency corresponding to the absorbed photon. So the mechanism is internal conversion and vibrational relaxation. These two processes are responsible for absorbing low energy photon. Then also from here you can go for an intersystem crossing. That is, you go from one spin multiplicity state to another spin multiplicity state. That is, you go from S1 singlet state to a triplet state, whereas here it goes internal conversion within the singlet states. Here is intersystem crossing. It goes from singlet to triplet states. Emission of photons from S1 to S0 relaxation, and it occurs in a thermally equilibrated excited state. Intersystem crossing is a non-radiative transition to isoenergetic vibration levels of electronic states. Different multiplicity, that is intersystem crossing. Time scale goes from few microseconds to nanoseconds. Phosphorescence emission from a triplet state to a singlet state shift to the longer wavelength relative to the fluorescence. Okay. So this is what one can just plot an absorption spectrum and an emission spectrum. So the emission spectrum is almost like a mirror image of your absorption spectrum. So if you measure them, a big shift, that is the absorption maximum, is the emission maximum. So there is a difference to give the Stokes shift. So the Stokes shift is an important parameter that gives signatures associated with the fluorescence. That is, due to solvent effects and excited state reactions, this Stokes shift may be shifted. So the mechanisms which are happening in the excited state may not be unique, may not be the same in all molecules. So it may be different. So when it differs, the shift, the Stokes shift, will differ from one solvent to another solvent. If the perfect mirror image rule is there, if the perfect mirror image is there, that means the configuration of the molecule remains the same in the excited state. That is, it does not make any excited state reactions, or the vibrational levels, difference between vibration levels is similar both in the ground and excited states. If you have a deviation from the mirror image rule, that means you have the configuration is different geometric arrangements and excited state reactions. That is what you can have. So in the excited state, you have a fluorescence emission, internal conversion, intramolecular charge transfer, there can be a conformational change, and an electron transfer. And if there is a proton in the molecule which can be moved, there is a proton transfer. There is an energy transfer, that is a collisional energy transfer, and excimer formation in the excited state. In the ground state, it may be a single molecule. When it becomes in the excited state, it forms a dimer, that is the excited state dimer formation. And exciplex, that is in the excited state, it forms a complex, then it is called exciplex formation, then the photochemical transformation. So all these things, the excited state reactions which you have, conformational change, electron transfer, proton transfer, energy transfer, excimer formation, exciplex formation, photochemical transformation, all will make you to differ from the mirror image. So the stroke shift will not be the same in all cases. It all depends upon the excited state reactions, or it all depends upon the environment around the molecule. So I am just showing a fluorescence. So it is benzene, acetonitrile, ethanol, DMF, DMF. So redshift. So it goes from around 525 to, it goes from 525 to, you just put at 575 or just around 570. So it goes redshift with respect to the non-polar solvent. And you don't see any dual fluorescence in the excited state. So it shows the absence of excited state intramolecular proton transfer. Actually, it's the same one when you have the excited state, you don't see the weakly structures, and there is no dual fluorescence. When there is a dual fluorescence, that means that you have two components that the emission takes from the two states, and the two states may be corresponding to them, one normal state and another corresponding to any intramolecular or a proton transfer states. The structure of methylene blue, okay, it's a simple one, okay, and sodium glucosyl sulfate is a surfactant. When you have dissolved the surfactants in a medium, it may have one component like that. One component, there is an anionic head and the long hydrocarbon chain. Anionic head and there's a long hydrocarbon. Then there is a cut. This positive charge is here. And when you slowly increase the concentration of the sodium glucosyl sulfate, what happens? At one stage, it forms a network like this. It forms a network like that. That they call it as a micelle. So a micelle is formed depending upon the concentration. So that micelle plays a role, can play a role, because it forms a spherical shape. So it can incorporate your molecule inside, and it can change its fluorescent signatures, and which can be reduced to understand what is the micelle concentration at this value. So I try to understand a physical property. So because this particular physical property I measure at various concentration of the surfactant, it slowly changes, then suddenly it shoots up. So if you say that you have two slopes, and one particular, the intersection of the two slopes will give you a point on this that is called the critical micelle concentration. So a physical property changes, then it goes in an abrupt change when micelle is formed, or when it has attained a critical stage. Then after that, the physical property shows a different signature. So just like that, yesterday I told you, you dissolve 1 gram of sugar in 10 ml of water, 2 grams of sugar in 10 ml of water. But if you measure them, refractive index, that's a macroscopic property. You say that it shows a linear change. But if you are looking at the microscopically, sugar solution or whatever, they may form clusters. They form clusters, and at one stage, the cluster and behavior will be predominant on the some of the microscopic properties. Like that, if you have methanol, methanol always forms clusters and gets dissociated. You will not in a methanol solvent. You don't know that it has a pure single methanol molecule. So dissociated continuously, it changes. So this is a case, that's a methylene blue. If you look at the methylene blue dye, its fluorescence, it's measured for the y-axis I have not given. So 630 to 750. What I am trying to show is that the peak is not shifted. The peak is not shifted when you vary the polarity of the solvent. So I have not changed. I could not see any signature on the fluorescence peak with respect to the polarity of the solvent. This is a very important signature because when it changes with the solvent, then it is very difficult for me to understand critical micellar concentration. So there is no change in the fluorescence maximum, but what happens is only the intensity. What happens to the only the intensity? Okay. Now, I know that the fluorescence emission has polarization characteristics. So I try to evaluate just like your depolarization ratio you measure in Raman, I perpendicular divided by I parallel. Here also you can make a fluorescence polarization. So when you measure the fluorescence polarization, because I could not see any change in the wavelength, but I can see only the intensity variation. So I parallel measurements, I perpendicular measurements are taken. Here the formula is different. It's not I parallel, I perpendicular by I parallel. It's I perpendicular minus I parallel divided by I perpendicular plus I parallel. So the polarization is measured. You can see that at a particular concentration, see, increases, then it comes down and goes like this. Here it comes down, then suddenly starts increases, then reaches a value and goes like this, and starts comes like this, and slowly increases comes like that. So it is in a methanol, acetonitrile, water, DMF. So what I have seen, there is no shift in the position, no change in the shape, but the intensity changed. That is that physical property that I have taken the number of quantas emitted, the intensity, then I try to understand what is its polarization characteristics, like when the polarization measurement is made for parallel component and the perpendicular component and reduce the fluorescence polarization. So I could see that microscopically a changes occurs at this critical micellar concentration. So a simple sodium reducing surfactant, because normally you use a surfactant, surface active reagent for cleaning your glass or making your face to be beautiful by removing the oil. So at a critical micellar concentration, that is what when they create, when they synthesize, they should see that when the critical micellar concentration is attained. So when the critical micellar concentration is attained, then its activity is more. Its activity is more. So the fluorescence signature is changed. Now that is I have taken one component system, that is a sodium deuteracyl sulfate is taken. That is a one component. Now it's a binary liquid mixture. So it's a mixture of two liquids. When you have a one component is a larger proportion, then you call it a solvent. The another component, a smaller in amount, I call it as a solute. So I have two liquids. One behaves like a solvent, another behaves like a solute. When you change the concentration or the proportions of the solvent and solute, I can see that there is a change in the solubility and the change in the polarizability, change in the viscosity, and many other static and dynamic properties. But what is here is that the intermolecular force exists, that is between the solvent and the solute, between the two components. So there is the intermolecular, that bound together these molecules in liquid. That is, you have a liquid, so you have a molecules, they bound by the intermolecular forces. Now there are 4 types of intermolecular forces. That is dipole-dipole force, dipole-induced dipole force, London dispersion force, and hydrogen bonding force. Dipole-dipole. Dipoles of 2 molecules are mutually attracted. So dipole-dipole interaction leading to the different orientation of the molecules. Dipole-induced dipole. A polar molecule, polar liquid interacts with a non-polar liquid. Electric field associated with the permanent dipole of the polar liquid disturbs the electron distribution in a non-polar molecule, thereby inducing a temporary dipole in the system. So you can have a acetic acid and carbon. So you have a dipole-induced dipole interactions. Induced dipole, and so exists between molecules of 2 non-polar liquids. An instantaneous dipole induced by the movement of the electrons that induces another charge electron distribution in the nearby molecule. Hydrogen bonding force, attractive force, which binds the hydrogen atom of one molecule to the electronegative atom of the other molecule, is known as hydrogen bonding. So you have a hydroxyl group, and nearby you have another oxygen atom. So there's a OH hydrogen bond. So it naturally, okay. So you can do a fluorescence and optical absorption analysis. One is the solvent itself. That is A is the solvent A, and a fluorophore is mixed. Then we have measure, then solvent A with the solvent B, AB. So solvent A with the indicator, solvent B with the indicator, solvent A as well as solvent B with the probe, that is AB indicator. So here the indicator is the probe molecule. So in the indicator molecule is used to understand the intermolecular interactions, that is between the one solvent to other component, or one time one larger proportion will be the solvent, the smaller proportion will be the solid. But between them, as I told you, there will be dipole-dipole interaction, dipole-induced dipole interaction, induced dipole interactions, and hydrogen bond formation. So I have 2 components, A and B. So my indicator may interact with any one of them. That is what I call it a preferential solvation. Properties depend upon the solute-solvent interactions. This preferential solvation is a complex in mixed solvents than in pure solvents, because here you have 2 components, whereas in other case it's a single component, because you know that when we have a one component system, you know that it is a non-polar and polar protic and polar aprotic. When you have 2 components like acetonitrile and CCl4, one has a dipole moment, another has a negligible dipole moment. That is, one component can polarize, another component cannot polarize. So the solvation is different. It's complex in a mixed solvent. In a pure solvent, I put an indicator. So the local mole fraction and the bulk mole fraction will be the same. If we take a pure solvent single component system, the local mole fraction and the bulk mole fraction are the same. But in a binary mixtures, this need not happen. This need not be happened. So in binary mixtures, the local mole fraction will not be the same as your bulk mole fraction. The local mole fraction will be different. It depends upon the interaction between the solid solvent and solid solvent, and interaction between the solvent-solvent molecules. Because when you have a solid and solvent, the solid has a smaller proportion, and the solvent is a larger proportion. But when the solvent is larger proportion, like methanol, when the methanol concentration is high, definitely there will be methanol clusters will be formed. There you'll have solvent-solvent interactions. When methanol concentration is lower, then predominantly that will become the solid, other component will be the solvent. So the solvent component or the solid component, depending upon its nature, they may form a cluster. Once they form a cluster, definitely there comes a solvent-solvent interaction or the solid-solid interaction. So what you have to look at is the 3 directional way. One is the solid and solvent interaction, solid-solid interaction, and solvent-solvent interaction. So the probe molecules can interact differently with the 2 solvents of binary mixtures. Okay, what happens covering a solid molecule with the overcoat of a solvent molecule? So the solvation, the solute particle is being covered by an overcoat of the solvent molecules. There's a solvation cell. Each molecule of the solvent is held in the vicinity of that solute molecule. Each molecule of the solvent is held in the vicinity of a solute molecule. That's a solvation shell. That is there. Solvent with the strongest interaction with the probe molecule. That means when it has a strong interaction with the probe molecule, more concentration in the cell. So the probe molecule solvation, the probe molecule has an interaction with one solvent, means in the solvation cell, probe molecule will have more number of the solvent molecules. That is, suppose X is the indicator and it has a strong interaction with the A solvent. So in the solvation cell, A solvent molecules will be there compared to the B solvent molecules. So solvation cell differs from the bulk solvation concentration. So selective concentration or enrichment of one solvation pair of probe molecule. All these things are very important. And the binary mixtures, its a methodology is slightly complicated, but one has to understand from the spectroscopic data which the solid prefers which solvation microsphere. So here you have a dihydroxyanthraquinone. Here you can have a proton transfer state. This proton can be transferred here, so you can have an OH group. So it is an equilibrium state. So the probe molecule has an electron donating character. There's a 2-hydroxyl group. Eliminate the proton transfer more quickly. So the excited state proton transfer, when you excite it, this proton can transfer. So it has a charge transfer character with a great change in the molecular geometry. So when it comes here, the geometry is changed. So if we have the dual emission in CCl4, the intensity just right taken. So dual emission, locally excited state and proton transfer states coexist. That is, here you have two states. One is the locally excited state and the proton transfer states. Proton transfer state is lower in energy than the locally excited states. That is, here it is in the red region. Right, the same thing. Now we have I told you the CCl4, you have a dual characteristics. That is, you have a locally excited state and a proton transfer state. So now I have a mixture of polar aprotic solvent and a carbon tetrachloride. Okay. So I have this ratio, CCl4 and ACN. Slowly I have increased the ACN acetonitrile. This is the acetonitrile concentration as an increase. So now when this is at once CCl4 concentration is high, that means that is the solvent and is a solid. When an increased ACN concentration more, then it becomes the solvent, this becomes a solid. So when I change the ratios from 1:9 to 9:10, the indicator remains the same. Indicator is the dihydroxyanthraquinone. So what you have is the transition energy should show a linear fit. The transition energy should show a linear fit because these are two limits. It should show a linear fit, but it's not showing a linear fit. So it shows something, it comes, decreases the energy transition, both absorption and the emission and absorption. So it's added to CCl4 and CCl4 rich. Addition of ACN increases and reaches to the value in the fit of the neat acetonitrile. So it decreases, then increases, comes to the neat acetonitrile. So here you can see a preferential solvation. That is, it not following a linear fit. It comes down when it acetonitrile is added, it decreased, then it reaches flat, then now this acetonitrile concentration is more, so it's moved through the solvation cell consisting of acetonitrate. CCl4 DMF mixture, this is a different case in which here is CCl4 and DMF. This the straight line fit, it's expected, but it is not coming like this. So addition of deviation from the calculated binary mixture till it comes to 0.6, then it comes here. So approaches the ideal mixture to DMF rich region. So in this case only, you have the local and bulk mole fractions are approximately equal. CCl4 rich region, solid molecule prefer to solvate, even though it's rich, it tries to prefer to solvate by the DMF molecule. Yeah, DMF has a high dielectric enrichment, so it gets attracted towards a more polar environment. It's a similarity here. It gets more attracted to the more polar environment. So here it's CHCl3 methanol. So both are, one is polar protic solvent, another is polar aprotic solvent. Now you see it's a linear fit. It's not showing a linear fit. It shows something coming down and going up like this. It's a dual behavior. Deviation from linearity, that is a CH rich region. Addition of methanol, decrease in U2 till the mole fraction comes to 0.6. Addition of methanol increases the value of 1. Solid prefers methanol over CH3 to get solvated here. So there is a competition between the solid solvent and solvent-solvent interaction. That is because both are polar, both are dielectrically rich environment. So there is a competition between the solid solvent and the solvent-solvent, because when it comes to methanol, it forms a cluster. So there is a solvent-solvent interaction. So that is why when it goes increasing, then because the methanol molecules are less here, when it starts to increase, it comes to them coming down. So here it is the solvent-solvent interaction is dominant. So 1,5-diaminoanthraquinone. So I just okay. Now I come to a point as molecular recognition. That is a specific interaction between two or more molecules. Calixarenes, just like a molecular basket by macroscopic receptor molecules, cyclic arrays of phenol moieties linked by methylene groups. So it is a cyclic one. It's a molecular baskets. So earlier I told about sodium uracil sulfate. There it's all anionic head and there's a long hydrocarbon chain. But when you increase the concentration, then only they form a spherical in shape. But here it is something like a molecular basket, and you have 4 phenol units connected via methylene groups, bridges, orthobenzene, and your hydroxyl groups are here like this. Now I have dichloromethylaminoanthraquinone. These are methyl groups like this. So now this 1:9. So tertiary butyl calixarine and the di. So the calixarine ratio is unit is 1, it's 9, and slowly changed because here it's calixarine concentration is high and the fluorophore concentration is less. Now you can see in tetrabutyl calixarine rich region, that is here 245 nanometer, it goes to a blue shift. This peak with the calixarine low region, it comes to 245. It shows a blue shift, whereas the 275 it shows a red shift. So one peak shows a blue shift, another peak shows a red shift, and of course basically dichloromethylamino region, which region they can see that increase in the intensity, because here the 9 it is 1:9. So here this one we have the fluorophore is high, whereas here the fluorophore is low. The concentration of the fluorophore is low. So the certain definitely the concentration will, the intensity will be more and the intensity will be less. There is nowhere connected with your intensity, but it is connected with the shift in the frequencies. So no new absorption band is formed. That means there is no possibility of formation of a charge complex between the calixarine and your indicator or your fluorophore. If there is a formation of a complex, then the signature will be different. Our case, there is, it should not be formed. The complex should not be formed. So now I say the absorption characteristics at the Delhi at 275 nanometer, mole fraction. So just a small calculation. So it shows at 0.39, it increases, then it comes down and increases. At 0.3 mole fraction of tertiary indicating the formation of 1:2 complexes. That means that just like what I told in the sodium glucosate sulfate, the mole fraction is a 0.4, then there is a small signature variation. So it increases, then it comes down like this. So again, I look at the emission, that is the absorption, the emission, and the intensity variation. So maximum intensity variation proves the possibility of interaction between them. So here is also shift, but here you can say the intensity variation. Blue shift is minimum in dichloromethylaminoquinone rich region, and it's maximum in the tertiary butyl rich region. That is, you go from this region. So this is the blue shift. Okay. So this is the blue shift because the calixary rich region. From here it goes to the blue shift. So lack of isoMSC point, possibility of interaction between more than one molecule is even is there is a lack of isoMSC point. So that means there's a possibility of interaction between more than one molecule of dichloromethylaminoanthraquinone with one molecule of tertiary butyl or vice versa. Okay, so also you can make the ratio between this pure one, that is the indicator alone, solvent and a solvent, the same solvent with tertiary butyl F by F naught. You can see that at 0.4 mole fraction, you see the fluorescence intensity changed. Okay, now what you have is that the molecular dimension of tertiary butyl is 3 by 2 Armstrong. So the cavity of the tertiary butyl is too small to include 2 dichloromethylamino molecules. This rules out the possibility of dichloromethylamino to be included in the tertiary butyl that basket. So the 2 molecules cannot go inside their baskets. So they are just attached at the bottom of the hydroxyl group. So interaction goes through the intermolecular hydrogen bonding between the hydroxyl group in the lower rim of the tertiary butyl and the carbonyl group of the guest molecule. So something you have a carbonyl group. So there's a hydrogen bonding interaction between them. So here it is done. So there's an indicator here with one hydroxyl group, another indicator is here. This is a Gaussian software which is reduced. So an experiment, then of course it's I have not given full details because we have measured the polarization, anisotropy, polarization, and polarization character P0 and anisotropy, that is which revolves around the orientation of the molecule. Then here instead of you have 4, you have 8 units. That's the guest molecule is 1,5-diaminoanthraquinone, and you have a host molecule which has 8 units. And so here is the calixarine 9 and 1,5 is 1 unit. So it is 9 to 1. 3 absorption bands are 241, 291, 475. And optical is decreased with increasing concentration of the dye. So the optical density decreased for the 291. This one decreased on increasing the concentration of the dye. Basically, it should have increased, but it has decreased. That means there is some signature is happening, and there is a blue shift from you go from this 291 and it comes around to 75. That's a blue shift, and there is no new absorption band. That's rules out a charge transfer complex between the guest and host molecules. And again, you make the delta A variation at 291 nanometers, and the mole fraction, you find the 1:1. The stoichiometry ratio of the complexation is 1:1 because it's 0.4. And fluorescence spectra of the calixarine. So you have a calixarine 1 and 9. Calixarine concentration, fluorescence magnitude 546. Fluorescence quenching happens. Of the binding of the 1,5 with the calixarine on increasing the concentration of the host, because you increase the calixarine concentration happens. Absence of isoMSC point, it suggests that there's an interaction between the more than one guest molecule with the more than one molecule of the host. So it is again 5.3 into 7.4 Armstrong. The intracavity size is 8.6 Armstrong. So then the two guest molecules cannot go inside. So one probable is that a pinched cone conformation, something, so if you have like that. So intermolecular hydrogen bonding between the carbonyl oxygen of the guest and the hydroxyl molecule of the positive group. So what I have suggested is that a simple experiment, maybe for the sake of students, I have given only a small piece of it. So electronic spectroscopy, you just take an optical absorption and the fluorescence. One is the absorption and the emission. So when you make the environment change, that is, you go from a non-polar solvent to polar solvent, definitely they can influence the ground state phenomenon, also the excited state phenomenon. So you can see even the optical absorption, you go from blue region to yellow region. So in the emission also, you can see the shift, a blue shift or red shift. It's a single component system is much easier. So one typical example is sodium deuteracyl sulfate, where a surfactant is a single component. When you increase the concentration, it forms a micellate that is spherical in shape. And when it has a critical micellate that's a spherical in shape configuration, it can alter the physical property of the indicator. So we have taken a fluorophore, that is the indicator, and monitor the emission, because we could not see any change in the fluorescence, any change in the fluorescence peak with respect to the solvent, only change in the fluorescence emission. So you can do a fluorescence polarization, fluorescence anisotropic studies. Then you have seen that it shows signature at its the critical micellate concentration of the sodium deuteracyl sulfate. Now you mix a two-component system, A and B, and the probe indicator can prefer A or B depending upon its interaction or the dielectric enrichment, and that all will reflect either in optical absorption or the fluorescence emission spectral data. The third case is what you are saying is a molecular baskets in which an indicator is involved, and you make a various concentration and do the optical absorption and measurements and the fluorescence measurements. And you can do the plot between the delta against the concentration, or F by F naught against the concentration, or the mole fraction of tertiary butyl, you can find at 0.4. So then you can understand this the interaction between the guest molecule and the host molecule. But there are various parameters which we have reduced that I will not make a presentation here, because that gives a lot of other data. Because so for sake of students, I just gave a small piece, a small part of the work of 3 of my PhD students. So this is a sentence I always like it. There is no end to the adventures that we can have if only we seek them with our eyes open. So whatever I have made in presentations, these are all done maybe some 15 years back by my PhD students. Thank you very much. Hello.
Thank you, sir.
This session is open for discussion. Participants are requested to post your questions in the chat box. Sir, there is no questions in the chat box, sir.
Okay, no, there is no question on the chat box.
Thank you, sir.
Okay.
It's time for lunch break, and we will join the next session at 1:45 p.m.
Thank you.
sir.
Thank you.
Thank you
Okay,
very
okay.
much, Ramakrishnan.
Thank you, sir. Thank you. Thank you. Thank you.
Good. So I was listening, but I tried to type something, but it was
Okay.
muted, so I couldn't speak at that time. Anyhow, thank you very much for your very informative lectures. Thank
Thank you, sir. Thank you. Sir. Thank you.
you. Okay. Let's see.
Thank you, sir.
சார் வணக்கம் சார். இப்ப மியூட் பண்ணிட்டாங்க சார், அன்மியூட் பண்ணிட்டாங்க.
Yeah. Okay, வணக்கம் ஜெகநாதன். Thanks for coming. Okay.
Good afternoon, everyone. We'll start the session. I invite Dr. M. INR, Assistant Professor, to introduce our speaker.
Good afternoon to one and all. Yeah, then start video. Good afternoon to one and all. I am happy to introduce today's chief guest, Dr. K. Jaganathan, as Department of Physics, Bhardas University, Trichy. He has 23 years of research experience. His research interests have spanned many areas over the years of including nanotechnology, nanowires, photovoltaic cells, drug deliveries, and many biomolecules on which he has published more than 120 papers in reputed national and international journals. He has participated many national and international conferences, and also he conducted many conferences. He is the director of Russo project. It is worth of 35 lakhs. So far, he guided 6 PhD scholars, and 7 scholars are doing their PhD under the guidance of Dr. K. Jaganathan. He has successfully completed 7 major projects, and he is doing 3 projects at the present. He has received many countries, and he is the professor with excellence academic record and leadership of the administrative capacitance. I hand out this section to Dr. K. Jaganathan sir. Welcome, sir. Thank you.
Thank you, Dr. INR. So very pleasant. So good afternoon to one and all. So I will continue my second lecture. I extend a warm welcome to every one of you for this second lecture. So in today's lecture, I'm going to focus on application perspective of one-dimensional semiconductor nanowires. So in the first lecture, I have covered some basics of semiconductors and what are the applications of low-dimensional structures and what is the underlying physics. So in nanomaterials are particularly the quantum structure. So in this lecture, let me briefly give you about the overview of nanowires and what are the interesting features of the nanowires, semiconducting nanowires particularly, and how these materials can be synthesized by different approaches, and what are the applications of those materials, in a specific emphasis on the photocatalytic water splitting, using the semiconducting nanowires as a future fuel of hydrogen. So we all well know about the low-dimensional structures can be fabricated either by bottom-up as well as top-down approaches. So in the top-down approach, simply you can take a bulk material, and bulk material, as you all know, can be represented with the dimensional coordinates of x, y, z. And specific to our requirement, just you can slice down the material, then possibly you may end up with having a one-dimensional nanostructures, two-dimensional sheet-like structures, and it's a three-dimensional nano particle. The same low-dimensional structures, 1D, 2D, 3D, can also be fabricated by bottom-up approaches. So as far as the low-dimensional structures or the nanostructures are concerned, so at least any one of the dimension of the material it has to be restricted to below 100 nanometers. In generally, if you take a bulk material, so bulk materials, no dimension at the nanoscale. So where you can see all dimensions are at the macroscopic scale. So for instance, if you look at the graphite, so you know well about the graphite, it's a very grand old material having extensive industrial applications, and also it has helped us to understand so a lot of physics. So here, this bulk form of your graphite has a stacked carbon layers. Your sheets of carbon layers are stacked together, so forming a black crystalline substances. So here the sheets, the carbon layers are weakly held by the van der Waals forces, so that you may able to peel off a sheet of carbon layer from the graphite. So when you have a single sheet or it's a few layers of sheet, it's called as a graphene. So these graphene sheets are the two-dimensional structures. So because the thickness is restricted, the thickness of the sheet it's about only 3.3 angstrom. It's very thinnest material of the world of known bodies. So whereas X and Y dimensions are in the macroscopic scale, or even it could be microscopic scale, does not matter. So here we bother about only the thickness of the layer. So as the thickness is very thin and an atom thick layer, this is called as the graphene. This has very interesting and intriguing properties. Well, again, the same sheet, right, can be rolled to produce the carbon nanotube. So you can again take this two-dimensional sheet, just use scramble it in a particular directions, you will end up with the fullerene-like structures. So the fullerene-like structures has a 0 dimension because all 3 dimensions of this carbon matter are restricted to the nanoscale or at the nanoscale dimensions, right? So here in carbon nanostructures, so the two-dimensional graphene is the building block of all low-dimensional structures of the carbon, right? So in principle, so you can have these low-dimensional 1D, 2D, and then it's either you can call it as a 0-dimensional nanostructures or 3-dimensional nanostructures. So because even the 0-dimensional structure has the dimensions spread along X, Y, Z directions. Simply in order to distinguish from the bulk part of a material, so we do call them as a 0-dimensional nano structures. So for this groundbreaking discovery of graphene, a professor at Manchester University, Andrew Jim, and his young postdoctoral fellow, so Costo Novovello, has employed a very simple and it's a conventional approach to peel off a sheet of graphene from a graphite by employing a Scotch tape method. So as I mentioned that the sheets of carbon layers are weakly held by van der Waals forces, so having only sp2 hybridizations, right? This is a very weak interactions. But on the other hand, a sheet of carbon layer has sp2 hybridized bonding in in-plane directions, having honeycomb hexagonal-like pattern. So this having a sigma bond in plane, this is very strongest plane. So graphene is very strongest, right? But not the hardest material, but it's very strongest material. So you cannot tear off this graphene sheet because the carbon-carbon bonding in graphene is equal to the bonding strength of the carbon in diamond materials, right? So it's a being very thinnest material. The physicist and chemist use this material to understand a lot of physics and then chemistry involved in this graphene. So for the discovery of this graphene, these two eminent personalities were awarded a Nobel Prize in Physics in the year 2010, in the 2010, right? So, but of course, the graphene is a two-dimensional material. So here our focus on this lecture is about the nano wires, right? So as compared to all 3 dimensions of a structures, 1D, 2D, 3D, just we have seen in the previous slide. So as compared to all other low-dimensional structures. So the nano wires, right? So having a very high surface to volume ratio, and moreover, the nanowires whose diameter is very thin, so it could be used for the electrical conduction too. And these nanowires have unique electronic states, that the density of states, then the physical properties, which are significantly different from the bulk part of a material. So the fabrication of functional nano devices with small dimensions can possible. So besides using these nanowires to interconnect the devices, so this has the multifunctional properties and then approaches to realize the new functional devices. And further, these nanowires have unique capability to realize highly lattice mismatched substrates because the diameter is very thin. It's possible to grow it on any substrates which could withstand such a very high temperature, or at least the growth temperature that you are using to make these nanowires. So how you can define the nanowires? As you already know that nanowires are one-dimensional structures. So it can be defined as the structure that has a axial size, but constrained to the only tens of nanometer. So whereas the unconstrained longitudinal or the axial size. So the aspect ratio is one of the important parameter that determines the variance of the one-dimensional structures. Aspect ratio is taken from the length to the diameter. Simply you take the length of your wire and then divide with the diameter, that will give you some numerical number, right? So this number decides, so whether you would call this one-dimensional structure as a nanowires, or it's a nanorods, or a nano pillar, right? Or it's a nano viscous. So different names, or it's a technical names are used, that is with respect to the aspect ratio. So when you have a very long wires with a small, very thin diameter, so where you call it as the nano wires. So obviously, when the diameter of these wires are to the order of either it's a de Broglie wavelength or effective Bohr radii, so you could call them as the quantum wire. But the quantum wires have a very unique characteristics, both the density of states as well as the current conduction, because the quantum wires have a electron confinement. So there are different types of nano wires and nano rods are used in the literature. So, but of course, here you can see that all those have been illustrated here. So only the concern here, as long as the length of the wire is long and the diameter in any form is restricted to below 100 nanometers, you could call it as the one-dimensional nanostructures. That includes coaxial nanostructures, but then it's a metal oxide nanowires or nanotubes, nanopipes with hollows, and you can also make the heterostructures with the nano belt, nano ribbon, nano tapes, and so on, right? So still the list is to keep on adding, but you have to make sure that, so this has the longer length and then shorter diameter. The diameter is restricted to below 100 nanometer, right? So why nanowires? Why nanowires? As I already mentioned that, so the nanowires provides the researchers to make both the functional devices as well as to interconnect them in the integrated nano system. And obviously, in future nanoelectronic devices, this nanowires is going to play a bigger role as a building block of every devices that envisage near future. Well, so when we talk about the nanoelectronics, right, as I said that the nanowires is going to be the building block for the future nanoelectronic devices, right? So the Moore's law is a roadmap for the semiconductor industries. As I told in the last lecture, one of the founder of the Intel Corporation, Gordon Murray, in 1960s and 70s, so he proposed a classical empirical law or rule, so which roughly states that for every 18 to 24 months, the number of transistors in the circuit has to be doubled. At the same time, so if this happens over the period of 24 months, the price should also get reduced to half of it, right? So until now, so this Moore's law convention has been kept in phase, and all the semiconductor majors are being following this Moore's law. So by keeping the fact of Moore's law, the transistor dimension, because it ultimately puts a pressure on the miniaturization of the devices, the device size has gone to almost the theoretical limit. As industries, in particularly the microelectronic industries, sees that no more reduction in the size of the transistor or size of the electronic devices, right? So then people look that even some of the companies, right, the technologist has predicted that, so whether it's a Moore's law is dead or alive, right? So in fact, so Moore's law will neither die, but it's a continue to live forever. So when we change the type of material for making these, I mean, it's a microelectronic or it's an nanoelectronic devices. But as of now, everybody had agreed that the Moore's law is facing a red brick wall. It's a critical challenge, right? So in order to keep moving this Moore's law, because this being a roadmap for the semiconductor industries, because they need to have some roadmap for the next 10 years or 25, 20 years, right? So that it is expected that, so by moving from a planar bulk material to a low dimensional structures, at least this Moore's law's prediction can be kept in phase at least for next 50 years in the nanoelectronic regime, right? But however, by using a very thin two-dimensional materials, so even now people are making a very powerful, and also the large number of transistors are being packed in a single chip, right? So a couple of months back, there is a small startup company from USA. They designed the world's largest chip that has ever been built in this universe, even by using a silicon, right? They took the whole silicon wafer, they employed it's a different technology to fabricate the transistor. So on the given, I mean, it's a 4-inch wafer, I think. They have packed, it's about 2.6 trillion transistors together. Just you can imagine that. So 2.6 trillion transistor in one single chip, right? So this chip has been used in a world fastest computer, right? That is used to predict the artificial intelligence algorithm, and then for machine learning, right? This is designed by, it's a Cerebras, and this chip was manufactured at Taiwan Semiconductor Manufacturing Consortium, right? So just you can see the power of transistor, right? So that is being used in the artificial intelligence algorithm, so which had been used to develop the vaccine for the COVID virus. So as we talk about the nanowires, as I told you that the nanowires diameter classically this should be restricted between 1 and 100 nanometers, right? So this having a very small diameter with the length of either it's a microns or it's a centimeter, meter, I don't mind it. So whatever be the longer length, right? So this could easily be fabricated on any crystalline or non-crystalline substances, right? So having a smaller diameter, the lattice mismatch is not a matter for these wires because it quickly get accommodated after a few tens of nanometers of wire were grown. But on the other hand, when you consider about the planar thin films or the epitaxial semiconductor epitaxial layers, when you wish to grow those layers on the crystalline substrates, so the foremost requirement is that you should look into the lattice parameter of your substrate as well as the layer to be grown. So when you have a large lattice mismatch between your substrate and then layer, then it's a very challenge to grow a single crystalline thin films, or so-called it's a epitaxial layer. So depending upon the lattice parameter to value, your layer should undergo either it's a compressive strain or the tensile strain. In both the cases, in the lattice mismatch cases, you always end up with having more defect at the interfaces, right? So besides this lattice mismatch, right? So the thermal difference, the thermal expansion and then thermal contraction coefficient, but also influences the quality of your layer. So when you have a different thermal expansion and then thermal contraction coefficient with respect to your substrate and then your layer, again more defects and then stress and strain are being introduced, right? So hence, as we have more advantage of nanowires, as it would be grown easily onto any lattice mismatch substrates. So then if you able to grow these nanowires of different dimensions with the different materials, right? So you can integrate these nanowires into the existing well-matured silicon technology, because the silicon technology is a well-matured one. The entire microelectronic industries are being focused only on the silicon-based material, because they have invested billions and billions of dollars for this technology. So those companies are hesitant to move to another platform, right? So then there is a possibility that the nanowires can be integrated with the existing silicon technology for the future nanoelectronic devices, right? So considering the significance and the importance of the nanowires, the world's biggest semiconductor majors like Intel, IBM, HP, and DSMC, right? They have got more interest on the nano wire-based devices, as in particularly the Gordon Morris semiconductor roadmap is at the challenging space, right? So the nanowires would help us to increase the density as well as the transistor speed. So obviously, as you are having it's a low dimensional nano systems, this will reduce the voltage required for your operation of your device, right? So when you look back your desktop computer, right? So you are having a very bigger SMBS power supply. Though your chip CPU is a very tiny, so that has billions of transistors, right? So you need a very huge power supply to power up your CPU. At the same time, when you give it too much of input, obviously a lot of heat are generated. The heat has to be appropriately dissipated, otherwise your device will fail in short span of time. So considering the significance of these nano wires for the technological advancement, and this have more flexibility than the planar frames, it's possible to integrate with the broad varieties of material combinations. Thus, the nanowires are emerging as a very powerful platform, not only for nanoelectronics, but also for in biological applications. So where you can envisage or you can do a low-cost genome sequences of biological and particularly DNA molecule. So needless to say that the semiconducting nanowires based FETs are also being fabricated in the laboratory, right? So and truly this has become a tool for drug discovery, detection of DNA, RNA molecules, and also the detection of even a single molecule, and also a virus can be detected using the nanowire-based field effect transistors, right? So, but on the other hand, the physics point of view, right? So when you look at the nanowires, the nanowires are having a smaller diameter. The diameter of the nanowire, right, are going to be the shorter than the mean free path of the charge carriers. So when you are using these nanowires for the charge transport, the carrier transport, the charges are traveling at the Fermi velocity. So this will never experience any scattering. So and then this transport truly become a ballistic transport. So without losing the momentum of electron or holes in the devices, so that for the functionality, the performance of devices made out of the nanowires will have a better performance than the planar made or the device made out of the bulk material. Just you look at the top one. So it's a macroscopic or it's applicable to microscopic system. So where the electrons are traveling. So as the length of the system is greater than the mean free path of the charge carriers, so the carriers traveling in the lattice of your material likely to undergo a collision with the other electrons of the atom, right? This collision obviously reduces the drift of the velocity of the charge carriers. So such kind of transport in a bulk material, microscopic or macroscopic system are said to be the diffusive transport, right? So besides the transport of the charge carrier along the axial directions, so when you're able to make a very tiny but highly packed nanowires, so which are standing vertically, the nanowire matrix are having its densely packed wires. So when you shine a photon on this materials, right? So these nanowires could improve the light absorption. So thanks to the matrix as well as the anti-reflective property. So the anti-reflective behavior arises due to the geometry of the nanowires. So here you are having an air gap. When the photon enters into this structure, the photon undergo a multiple scattering, like a total internal reflection will occur, right? So all the photons which falls on this structure get absorbed by these nano wires having a sufficient length. At the same time, as a result of photon absorption, the excitation taking place, or I would say the electron hole pairs are generated. These the electron hole pair generated in the system as a result of photon absorption, right? So allows the material system, but allows the decoupling of photon with the carriers, because the photons are said to propagate in the axial directions, whereas the charges get migrated in the radial directions. So here the photon and then the minority carriers totally it's a decouples photons and then charge carriers, right? So that the photons and then charge carriers are orthogonally linked in this system, so that you will never see any interaction of the photons with the charge carrier, but once they are created, right? This is very interesting observations, which means that when these nanowires are used for light harvesting applications, certainly it's possible to increase the performance or efficiency several fold better than the planar structure. As the semiconducting nanowires are concerned, right? So you can make the varieties of nanowires. So here I have more interest towards indium gallium nitride. So indium gallium nitride is a wide bandgap semiconductors. I'll be having more slides about indium gallium nitride and nitride based materials. So here with this alloyed semiconductor, it's possible to tune the bandgap from 0.7 to 3.4 electron volt. If you look at the solar spectrum, so the given indium composition of 0 to 40% would be able to cover the entire visible part of the electromagnetic spectrum or in the solar spectrum. And moreover, these materials, indium gallium nitride, are chemically very, very stable and non-toxic to living system, and being a very transparent to the from UV to IR region. And these materials are having very stable electrical and then optical characteristics even at elevated temperatures. So besides all these characteristics, this indium gallium nitride material has more radiation tolerance than any multi-junction 3-5 solar cell technologies that are being used in the space quality solar cell applications. So truly that these are materials of choice not only on optoelectronic devices, but also for energy harvesting or particularly the solar cell applications, right? However, these materials, indium gallium nitride, as you can use this for solar cell applications, so you have to grow this indium gallium nitride as an active material to a thickness of several micrometers, right? So this indium gallium nitride does not have any native substrates. You have to grow only on your foreign substrate. So the lattice mismatch is a great challenge or issue here in growing the heterostructures, right? So and further, but increasing the composition is also very challenging, because this creates, because of the phase diagram limitations, as you try to mix three different elements to form a compound single material. It's alloyed material. So again, there is a large miscibility gap exists. It undergoes the phase separation of indium nitride and then gallium nitride. And moreover, the high binding and thermal energies of nitride with the metals forbids of growing a very thick layer, right? So thus, obviously, the conversion efficiency is very limited when you are trying to use indium gallium nitride for solar cell applications. But on the other hand, by employing these material in the nano-dimensional form, particularly in the nano wires, so this could help us to overcome the difficulties that you have encountered in the manufacturing or it's a fabrication of silicon nanowires. I mean, it's a silicon indium gallium nitride solar cell, but using indium gallium nitride based material. So no doubt that the nanowires are emerging as a new platform for solar cell applications. So because it is having an increased surface to volume ratio, because more photons can be absorbed to the surface of the nanowires, having it's a better photon absorption, and because of the geometry matrix of the nanowires, which reduces the reflectivity, so which allows the efficient electron charge transport, and having it's a further reduced recombination. So the Shockley-Quasier limit can also be overcome in this nanowire with the geometry of the solar cells, right? So further allows us to realize two-dimensional semi-quantum confinement of the charge carriers. But as you keep the size of the nanowires or to the at least near to the quantum confinement regime, right? So these nanowires can be made either into the lateral heterostructure or it's a core shell heterostructure. So in order to reap the benefits of the surface to volume ratio, it's a large surface area towards them, converting all the photons into the photo-generated charge carriers, you can make the core shell radial nanowires. So where certainly you can reach the theoretical efficiency of greater than 50% by having the indium composition from 0 to 40%. Well, so to grow these nanowires, so we are employing chemical vapor deposition approach in our laboratory. So this is a setup we are having in our university. So here you can see that this is a two-zone furnace. So where it's capable of heating up to 1200 degrees centigrade. The reactor is designed with the quartz tube. So where each ends of the quartz tube, quartz reactor are fitted with the vacuum tight flange, right? So having appropriate, these flanges have appropriate feed through. So where you can feed your carrier gas as well as the precursor. So this is the illustration of our CVD reactor, right? So the flow of gases are controlled through a mass flow controller. The source is taken here in order to grow a gallium nitride. So we use gallium as metal, high pure metal gallium as a precursor. So the gallium is taken in a tiny quartz crucible, and the substrate is placed in the downstream of the gallium source. So when you heat the gallium, it produces a vapor. These vapors are transported using a carrier gas to the substrate region. So where we use silicon as a substrate to grow these wires, right? So under a certain growth parameters, you can grow them as a different types of nanowires. As far as the CVD process or the reaction kinetics are concerned, in a moment if you transport the reactant gas using a carrier gas, it undergoes a transportation followed by on the heated substrate, your precursor molecules are got absorbed onto the substrate surface. So because of the sufficient thermal energy, the reaction takes place, right? So where you are having the radicals or the atoms are formed by these reactions. So while the unwanted ligands are separated, the radicals are the ligands are dissolved from the substrate surface. So here these radicals, right, the precursor radicals or so-called atoms are become highly energetic, and these tend to diffuse onto the substrate, or it's a migrate onto the substrate surface until to find a favorable place to form a nucleations, right? So when the Gibbs free energy is got a minimum, right, the nucleation takes place, right? So depending upon the lattice conditions, right, that is pertaining to the interfacial energy, right? So the different growth modes takes place during early stage of nucleations. So when your substrate and then the material to be grown is the same of the chemical composition, right, having its homoepitaxial structure, right? So where the lattice mismatch is nil almost, so this will undergo a Frank van der Waals growth mode. So where this will, all the nucleations get coalesced to have its a continuous layer growth. So if you have a large lattice mismatch, right, the wetting is poor, there is a localized nucleation will take place. This allows to grow as a islands or as a wire, right? Such growth mechanism is called as the Waldmer-Weber growth mode. So when the layer as well as the island growth are mixed together, so you are realizing it's a new growth mode where your thin layers are undergoing a compressive stress, right? So as the increase of the thickness of the layer, this compressively stressed layer get relaxed, so forming a droplets or the it's a dots on the surface of your layer, right? So where you can use this approach to grow the quantum dots. So such a method is called as the Transky-Krasnow growth mode, right? So by controlling these growth modes, right, you can grow the desired morphology of the nanostructures you are interested, right? So here my interest lies on making the nanowires. I do prefer to grow the wires with the Waldmer-Weber growth approach. So as you look into the 3 nitride system, right? So just to look at the periodic table, right? You can see a group 3 elements such as indium, gallium, and aluminum. And these metals are bonded with the nitrogen, right? This forms a different binaries such as indium nitride, gallium nitride, aluminum nitride. These 3 binaries are called as the wide bandgap semiconductors, right? So this has that band gap span from 0.7. Indium nitride is a 0.7. Aluminum nitride having got 6.2 electron volt as a band gap. So while gallium nitride is 3.34 electron volt, right? So if you look at this chart, it's a lattice constant versus band gap or the wavelength, right? So by connecting these 3 binaries, you can understand that so the band gap can be tuned from 0.7 to 6.2 electron volt by alloying either 2 binaries, right? Alloying all 3 binaries, it's possible to change the band gap in this wide regions. So by comparing with the other material system, either it's a group 3,5 materials or it's a 2,6 materials, it certainly allows, right? It's an advantage that this is the only material system which would be able to cover the entire region of the visible part and also spanning from infrared to deep ultraviolet, right? So these, when gallium nitride alloyed with the indium nitride with the appropriate composition of around 20% indium, this material emits a intense blue light, right? So the LEDs are being fabricated, all the commercially available LED as of now, which emits a light in the blue as well as in the white regions, are being fabricated only out of indium gallium nitride. So these are materials of the choice, so industrial choice for growing the light emitting diodes, and also it's a backlighting for your mobile phones, backlighting for your displays, that includes TV, monitor, and every thing. So not only it's a technologically, but also industrially, this is very, very important material system. So way back in before 1993, these 3 Japanese guys were working on the nitride system. These materials are known since 1960s. The basic properties were being extensively studied, but everybody had failed to grow a good quality of materials. But whereas these three guys, right? He's Professor Takasaki, of his students, Hiroshi, Ameno. So when these two were working at the Nagoya University, Japan, they accidentally discovered the P-type gallium nitride. So P-type gallium nitride was a very problematic one because of the poor activation, which forms a magnesium and then hydrogen complex. So where this guy, Suji Nakamura, as a young graduate, probably at the year of 20, so when he was assigned to grow the gallium nitride epitaxial layer by MOCVD, so he had changed the configuration of the MOCVD system. Then finally he was successful in growing gallium nitride, indium gallium nitride of N type with extremely very high quality. But still this guy could not make a P type. So where these two eminent personalities were successful in growing a P-type gallium nitride, the ideas were combined. So finally they made successful in growing PN junction based indium gallium nitride light emitting diodes. So for this groundbreaking discovery of indium gallium nitride light emitting devices or diodes, right? They were awarded a Nobel prize in physics in the year 2014. Right. So not only Japanese were working at the time, the entire world were started to work on the nitrides, but everyone had failed. Only these three people were succeeded in growing indium gallium nitride based light emitting devices. So because of the group work and then dedication. So we understood that the nitride systems are chemically very stable, non-toxic to living system, and having a stable characteristic at high temperature. This is the materials of the choice for various applications. So these nanowires, as I already mentioned, that can be grown by CVD by using either it's a catalytic or it's a self-catalytic approach. The catalytic approach begins with a very thin catalytic layer like a gold, nickel, or silver. So on a silicon substrates deposited by electron beam evaporation. Then when these substrates are annealed under vacuum conditions at very low temperature, so it forms a electric point having a liquid droplet, right? So you know the melting point of gold is around 1337 degrees centigrade, 0.3 degrees centigrade. But when it alloyed with the silicon, a portion of silicon is dissolved into a gold, the melting point of this alloy system was rapidly down to 363 degrees centigrade, where it forms a liquid alloy. Then by supplying your precursors of gallium and nitrogen, it allows you to grow the gallium nitride. So what happens that when gallium and indium goes inside a liquid droplet, it undergoes the what is that? The saturation and then to super saturation. Thus, the change in interfacial energy or the change in chemical potential allows the solidification at the solid interface. So then by continuous supply of the radicals, the nanowire grows in the one-dimensional manner. So where the presence of a liquid droplet activates the growth of the nanowire in a confined directions. Well, so the characteristics of the nanowires grown by VLS approach, you will always having a droplet on the tip of your wire. The presence of a droplet at the tip is an impurity. So in order to have its high quality devices free from such impurities, right? So you have to look for an alternate approach to grow these nanowires. So where we undertook a catalytic, self-catalytic approach, where we begin our growth with slightly gallium-rich conditions. So where this gallium acts as a balling effect, you know, the melting point of a gallium is very low. It always preferred to be having it's a liquid, I mean, it's a droplet. So because of it having a very high surface tension, then by supplying the precursors of one gallium as well as nitrogen, so it forms the gallium nitride. Even a one monolayer of gallium-rich condition is sufficient to promote this gallium nitride growth. So this is called as a self-catalytic approach. So here you can see the difference between the gallium nitride grown by catalytic and then self-catalytic approach. The nano is grown by self-catalytic approach, having it's a very clear hexagonal facets. There is no impurity like catalyst at the tip of a wire. So the grown gallium nitride nano wires can be used for various applications. So one such application that here I am focusing is for the photocatalytic splitting of water to produce the hydrogen gas, right? So why water splitting is essential, right? So why is it really required? So water is a dihydrogen oxygen. So having it's a 2 hydrogen and then 1 oxygen. So when you able to split, when you find a way to split water, you will get 2 hydrogen and then 1 oxygen. So this hydrogen can be used as a fuel for next generation transportation, right? So this is a known concept since long back. So where hydrogen can be used as a carrier gas for various industrial applications, right? So sometime back, right? So these hydrogen have been powered hydrogen based fuel cell. So wherein I mean it's used to transport the buses, the car, but it's a expensive avenue to use as of now. It's an expensive one to power your car or any transportation. So where by knowing the importance of the hydrogen as a gas, so it's expected to be it's a future energy carrier. So because of its high energy density, as compared to any other existing fuels as of now being used for the transportation purpose, or it's producing the power, whatever the applications, this hydrogen has a very high energy density. It's supposed to be twice than the natural gas, or it's a thrice of the gasoline gas, right? The usage of hydrogen for transportation applications, or it's a clean and then it's a green energy fuel, right? So hence this hydrogen can be used for the power generation, and also a small amount of hydrogen can be mixed with some other synthetic fuels, right, for various industrial applications. And also you can use these hydrogen gas for the industrial heating applications. And this hydrogen is also one of the important constituent for the ammonia synthesis. So in which hydrogen can be stored in the form of ammonia and being used for other industrial applications, right? As this hydrogen being a carbon emission free fuel for vehicles, it can be well stored in some advanced technologies. And also this as you can use this hydrogen for transportation applications. So this protects your environment so from greenhouse gases. So at presently there are various methods are available to produce these hydrogen gases. So some of them are the steam reforming, or it's a renewable liquid reforming, and it's a fermentation. These are the techniques widely used. It's about 99% of the hydrogen gas available as of now are being produced by these 3 methods. But these methods are energy intensive, and the byproducts of this process are carbon dioxide, carbon monoxide, and other pollutants that are being led to environment. So this harms our environment. It continue to pollute our mother nature. So in order to look for an alternative and then efficient approach, the only way is to split the water. It's electrolysis of water, so with very low potential. So the photoelectrochemical water splitting or the electrocatalytic water splitting is an efficient and very interesting approach to produce the hydrogen gas. So since this has get operated at a very low voltage, this very simple process as compared to the other listed one, and having its a low manufacturing cost, I think not now, but in future when you go for its mass production, and this will have certainly a high yield, and it can be extended for the commercial applications, right? So these hydrogen gases used as a carrier gas for the fuel cell technology to produce the electricity. Right? The fuel cells are having very high efficiency. However, you can use this hydrogen gas directly in the engine as like a gasoline, like a combustion process, but the yield, but this will produce very poor efficiency, right? So in order to use them directly for the engine, right? So the industries, I mean, it's the companies and other technologists are modifying the existing engines, right, to use it for the combustion applications. Anyway, we have to scientists have to go a long way to realize the direct combustion, even in addition to the fuel cell technology, because the storing hydrogen is a challenging issue as of now, right? So the hydrogen gas can be compressed and stored in a cylinder as like with other gases. Well, you can use for the stationary applications. So for mobile applications, for vehicle transportations, right? So probably hydrogen is one of the dangerous gases, right? So it will could explode. When explosion takes place from the cylinder, there will be a great devastation in and around that places. So to avoid that, the hydrogen people are trying to store using some metal hydroxides placed inside a cylinder. So where the high pressure hydrogen gas is being absorbed onto the surface of a metal hydrides. So when by heating, you can release the hydrogen by desorption process to power your fuel cell or for the combustion process. So once the hydrogen gas enters into an anode, it produces an electron. Then when this proton interact with the oxygen molecule, so which absorbed from air, this produces a water. So while electricity is being produced in the load, the byproduct in the fuel cell is only a water, right? This is harmless to our environment, where you start with the water, you end with the water, right? With some intermediate process, right? You can use water as a fuel for the next generation transportation applications. So the obvious question being asked, right? So whether hydrogen, the use of hydrogen gas is really it's a safe, right? So there are some experimental demonstrations, right? So hydrogens are lighter gas than the air. So when a leakage is taking place from any vehicle from the cylinder, in the event of fire, the hydrogen could easily escape from the vehicle to the atmosphere. So even if burning takes place, it's completely burned as a clean, and then it's a clean flame. Whereas gasoline, that includes petrol, diesel, so which are heavier than the molecule. So it leaks under the car, and in the case of accident, so it burns down your entire vehicle, right? So in newspaper, occasionally we are reading that several petrol diesel cars have got fire on the road on the midway, right? So this is one of the reason, and it's a poor safety in the tank leakage, right? There are several reasons are that, but so why that all of a sudden to burn the entire vehicle is due to that the gasolines are having, it's a heavier than air, so the burning takes place underneath your vehicle, down the vehicle, so it completely get cutted by the fire, right? Okay, so as you said that, you can ask me a question that as you said that, so this has all the eligibilities or the characteristic to use it for the I mean it's a technologies, right? So why it has not been used for as an energy carrier on large scale, right? Still we are in the experimental stage, and it's too expensive to implement hydrogen as a carrier gas, right? So and moreover, there is a heavy competition between the fossil fuel generators, and then it's a new energy generators, new energy generations, right? And moreover, it's a geopolitics, and then technopolitics, right, are not allowing the hydrogen energy to take forward, right? So it is possible that in future we would be able to overcome all these challenges, certainly the hydrogen energy will become a zero cost system, right? So then when will this hydrogen be ready to use? The hydrogen can be used even now for certain energy applications, for portable devices or stationary devices on the ground. But the technology is already developed enough to be able to use hydrogen for stationary applications and small electronic gadgets, right? So you would be reading the newspaper in every day, right? So the hydrogen vehicles, right, like a e-vehicle, or in the demonstrations on car, bus, boats, including ship, right? So probably in 1 or 2 decades at the maximum, right, you can own your car which run on a water, right? Okay. Now we will come to the issues of the splitting water, or how the water can be split in a simplest approach using the semiconductors, particularly the semiconductor nano wires, right? So you'll be knowing about the photosynthesis process. So the photosynthesis process is a naturally occurring, right? It's a very efficient, I mean, it's a very interesting process, right? So where in the presence of a sun in the plants and other micro organisms, right? So having its water and then it's a carbon dioxide, this generates its own fuel such as carbohydrates, right? Having its sugars. But at the same time, so when it generates its own fuel for the survival of these plants, the byproduct is the oxygen in the photosynthesis process. So the byproduct of oxygen is primarily responsible, right? So for keeping your atmosphere with the sufficient amount of oxygen intact. You might be knowing that. So when even a small, or it's a fraction of percentage of oxygen drops from the environment, right? I mean in the atmosphere, so we start to face a breathing issues. So when you climb the mountain, so where the oxygen levels are goes down, so there you can notice the breathing issues, right? The same manner, when the atmosphere oxygen percentage got reduced, right? So our life will be very miserable. So all the polluting gases, the greenhouse gases, right? It's polluting your atmosphere and also trying to reduce the oxygen content, right? So without the photosynthesis, right, you cannot keep your environment very clean. By having it's the same analogy of the photosynthesis process. So instead of plants and other microorganisms, you can use semiconductors as a medium to convert one form of energy, or it's a water-based, to another form of energy. It's a hydrogen. So hence, this process can be called as an artificial photosynthesis, right? So the naturally occurring photosynthesis is very interesting process, right? But this is not an efficient process. So where with the artificial photosynthesis, you can enhance the efficiency of the conversions. So because water has the energy of, in order to split water, you need 237 kilojoule per mole of water, right? So when you're able to supply this energy in the form of electrical energy or in the form of photo energy, in principle, it is able to split, right? But this is going to be an uphill process. So directly you cannot accomplish this process, right? So then you can take the route of photoelectrochemical water splitting approach. There you can use your anode and cathode being immersed in an electrolyte. This is simply an electrolysis process known by the chemist for over centuries, right? So here by applying a potential or by having a photon on the surface, right? So in order to absorb photons, we have to use the either it's an anode or cathode as in the form of a semiconductors. This was initially demonstrated in around 1971 or 72, right? Fujita and Honda in Japan, right? So this photoelectrochemical water splitting has become very interesting and popular among the researchers, right? They demonstrated with the titanium oxide titanium oxide would be able to absorb photon in the ultraviolet regions. So only a very small component, so less than 5% is available from the solar light. So whereas we have it's a huge amount of solar radiation in the visible regions. So appropriately, when you choose a semiconductors, so which will absorb the visible photons, right? So where this will undergo the absorption process. The absorption results the formation of electron and hole pair, and the electron and holes are separated appropriately. The electrons in the conduction band of a semiconductor undergoes a reduction process with the water, right? It's a producing electron in the circuit, and also the holes in the valence band get oxidized by the water, so producing the radicals such as super radicals along with the proton. So when the proton combined with the electron, it forms a hydrogen as well as oxygen, right? So thus, with the simple approach, you would be able to split water into hydrogen as well as the oxygen. The process involved in this process are half cell reactions. In the overall water splitting reactions, you need at least 1.23 volt to split 1 mole of water. Actually, this amount of energy is little high. So whereas the hydrogen evolution reaction can take place at the 0 volt, right? So people are experimenting with the various materials and then various catalysts to reduce this voltage level with improved efficiency of the water splitting. There are plenty of materials being experimented around the world, but still there is no magic material, or you cannot, even now we haven't identified a single material, right, which would split water efficiently with 100% efficiency, right? Still we are in the experimental stage. A lot of progress have been made with the various types of metals, metal oxides, semiconductors, and then functionalization of the metal semiconductors, right? But the process takes place in the photocatalytic water splitting, or the band gap absorption, separation migration, and then surface redox reactions, right? So gallium nitride was identified to be one of the very good material which satisfies the thermodynamics of water splitting. So where these gallium nitride based materials, right, have appropriate band edges, right? So this encompassing the water oxidation and then reduction the potential with respect to normal hydrogen electrode. So obviously nitrides are the best material to use it for the water splitting applications. As when you do use them in the nano wire form, all having its a vertical nano wires, or even in the form of entangled wires, all the photon which falls on that being absorbed by its band gap, and also the geometry that allows the anti-reflection of the photon undergoing the multiple scattering. So where I told that the photon and then the carrier generations are decoupled, right? So the minority carriers generated in these devices are not annihilated as a result of the smaller diameter of a wire. So all the photons contribute the conversion of or the formation of an electron hole pair. So thus you can have very high density of current generated by these nanowire based devices. So when these nanowires are used as an it's a electrode, either it's a photoanode or it's a cathode appropriately. So this it undergoes either it's a reduction as well as the oxidation process producing hydrogen as well as water in the respective surface of the electrode. So having split the water by this simple approach. So in order to understand the characteristics of this material, so just you can measure the current density with respect to applied potential. As the gallium nitride is concerned, as I mentioned, that this material will absorb more photons only in the ultraviolet region because of the band gap, 3.34 electron volt. But still, it responds to the visible photons So at about 0.5 but applied the potential, the current, the turn on, the device is put on, and then the current density increases with the increase of the potential, right? So we have tested this nano wires under dark light as well as in the chopped condition, and we have concluded that the gallium nitride is very stable material, but this is not a very efficient one. Then we have moved to the indium gallium nitride, so where you have the freedom to change or it's tune the band gap in the entire visible part of the electromagnetic spectrum. So we have graded the indium composition from 0 to around 40%, and we end up with having it's a n-tangled, very long nanowires. It's about 100 plus micrometer of the length. So with the average diameter of 45 nanometer. So when this indium gallium nitride was used as an electrode for photoelectrochemical water splitting approach, we found that so these nano wires absorbs photons, visible photons in the different wavelength region, so that we understood from the photoluminescence spectrum. We do also have characterized to understand to get the feedback of the material. So we found that, yeah, here you can see that. So this indium gallium nitride so gives out very high current density, right? So even at very near 0 volt, at below 0.25 volt, we found that the current density rose up to it's about 20 milliamps per centimeter square, and with the increase of the potential bias, the current density reaches maximum around 40 milliamps per centimeter square at applied potential of sorry, applied potential of 1.5 volt. So here, so in order to irradiate this indium gallium nitride, so we have used 100 watt xenon lamp, so replicating the solar spectrum with the condition of air mass 1.5 G filter, so which has the illumination irradiance of 100 milliwatt per centimeter square. So these conditions corroborates that there is a 1 sun irradiation on the surface of the nano wires. Well, so applied bias to photo current conversion efficiency is the benchmark efficiency which decides so how the electrodes are efficient to split the water, right? So we have done with various applied bias, and we have calculated the applied bias photon to current conversion efficiency. We observed that it's around 0.34 electron volt. The efficiency is 16%. So this is the highest ever reported for indium gallium nitride. We do have also experimented by changing the diameter of a wire, and with the grown the different conditions, we found that this efficiency even have gone up to 23% with very low potential. With low potential, the turn-on potential is also low. So we have also found that the stability of these nanowires are very good. This does not have much photo corrosions, but all our studies have confirmed that the gallium nitride, indium gallium nitride, is a very, very stable material. So for alkaline based water splitting applications. Well, I think I can go 5 more minutes. Let us turn our interest to two-dimensional materials, but graphene, but as a co-catalyst for the silicon-based nanowires. So silicon is one of the very interesting, and I mean, it's the materials are very cheap, and then high quality silicons are available for various good applications, right? So, but silicon has band gap is only 1.1 electron volt. The photo corrosion of silicon is very, very high. This is not a stable material. So against the electrolyte conditions, right? So in order to improve the characteristics of the silicon, in order to use for this water splitting applications, So we need to improve the characteristics of the silicon with appropriate co-catalyst or its a surface functionalization, right? The two-dimensional materials such as graphene and other transition metal, dichalcogenides, right, or other family of material are very interesting when it is functionalized with the silicon, so which will enhance the conversion efficiency. So we have used some kind of 2D materials such as molybdenum disulfide and then niobium disulfide as a co-catalyst. So in order to improve the characteristics of a silicon, and the silicon can get quickly oxidized, but when these are covered with those two-dimensional material, you can reduce or you can avoid the oxidation of a silicon. So for these water harvesting applications. So here we grew this silicon nanowires by very simple approach. It's called as the metal assisted chemical etching process. Just we start with the silver nitrate deposition on the surface of a silicon, right? So then this it's a silver nitrate is reduced to silver nano particle with the HF, hydrofluoric acid, right? So then by immersing this silver containing substrate into a electrolyte such as mixed with the HF and then H2O2 at the various concentration. H2O2 is a very strong oxidizing agent, right? So where this silicon is in contact with your this silver contact with your silicon surface, so provides an additional electron by this reactions. So where it quickly edges anisotropically, so like this manner, right? So where you have silicon, it's a silver on the silicon region get quickly etched away, right? So then here this silver is trapped between the one-dimensional structures, but by with the cleaning with the HNO3 several times, rinsing your sample, you could remove all these silver nano particle, right? So the silicon nanowires prepared this approach have been functionalized with MOS2 and then NBS2, and we have tested the efficiency of water splitting as in the case of gallium nitrate or indium gallium nitrate. So here you can see that. So the silicon nanowires covered with the NBS2, right? So have excellent characteristics. The device turn on even at very low potential at zero bias. Here you can see this delivers around 30 plus milliamps per centimeter square of current density, right? So having an appropriate functionalization on the silicon surface, it's possible to improve the water splitting efficiency. So where this is one of the simplest approach, so to realize a very high current density, so which will envisages higher it's the solar to hydrogen conversion efficiency, right? So the structure with MOS2 and then NBS2 covered with the silicon, right? So produces the current density at very low voltage of 0.3. So we are having 33 milliamps per centimeter square and then 35 milliamps per centimeter square, right? So this is one of the best value for the given silicon based materials. So however, here and there a lot of good results, better reports have been put there, but still the science as we are a scientist have to go a long way to realize for the practical applications in order to use water as a fuel. So to split the hydrogen from the water and then being used as a fuel for next generation transportation applications, right? So the targeted efficiency if is of 5% is sufficient. So if you're able to achieve this 5% of solar energy conversion, it's possible to run your own car on the water. As I told you that even several Indian I mean, it's a vehicle manufacturer, are also testing the usage of fuel cell buses on the Indian roads. I think a couple of months back, Tata has housed hydrogen fuel cell on one of their vehicle, and I think they have ran from Hosur to Bombay, somewhere else in a longer distance. So, but soon we can expect hydrogen fuel cell buses, but the buses will run from the water splitting will take more time, probably it's a decade or even more, right? So let me conclude my talk. So with that, maximum photocurrent conversion efficiency of 23% we have achieved with the indium gallium nitride nanowires. One-dimensional indium gallium nitride nanowires certainly is a emerging building blocks, not only for optoelectronic, but also a potential photocatalyst for the hydrogen evolution reactions. So before closing my talk, I thought of sharing the facilities that we have in our laboratory. So here at Bharathasan University, at Center for Nanoscience and Nanotechnology in the Department of Physics, so we have excellent facilities for the fabrication of various types of nanowires. That includes CVD, thermal coating, thermal evaporation, and RF DC magnetron sputtering, electron beam evaporation, and the rapid thermal annealing furnace, spin coating, and so on, many more. And also we have a setup for the device analysis and also characterizing them extensively. So with the scanning probe microscope, that is atomic force microscope, scanning electron microscope, variable temperature, photoluminescence, particle size analyzer, electrical probe station, electroluminescence, solar simulator, cyclic voltammetry, gas chromatography, and then xenon lamp. So we are also having the laser micro-Raman spectrometer, SCM spectrocoder. So soon we are adding these facilities. So in the Department of Physics or at the instrumentation center. So thank you very much. So for your kind patience. So if you have any questions and clarifications, so we will have a very short discussion.
Thank you for such an interesting session, sir. The session is open for discussion. Participants are requested to post your questions in the chat box. There is a question in the chat box, sir.
Okay.
Sir, please explain surface to volume ratio.
Yeah, surface to volume ratio in rising stars. Can outsiders make use of other facilities? Okay, the surface to volume ratio means, so when you make the size smaller and smaller, the more number of atoms are coming onto the surface, the atom occupying the volume at the bulk part of the material decreases, right? So when you take nano wires, so most of the atoms would reside on the surface of a wire, so only a minimum atom in the bulk part, right? So when you calculate the surface area with respect to the volume, so you will be having very high surface area with respect to volume. So the nanowires, among the three low dimensional structures, nanowires are having very high surface to volume ratio. So for instance, I can tell you that just you take a very big animal like an elephant, right? And you look for a mouse, right? So the mouse have got, it's a very small, poor animal. The surface area is very high as you account the volume. But when you look at turn your interest to the elephant, is a very big mammoth. The surface area is very small as compared to its volume. Likewise, any low dimensional structures, as you keep reduce the size of your matter, as more atoms are approaching on the surface, your surface area becomes very high as the volume will decrease. right? Okay, so switch off your video. Sorry, being late. Explain surface to volume ratio. Okay, rising the volume. Okay, outsiders. Yes. So some of our facilities are thrown open to outside users, right? So you can look into our web page. So where we have listed the extended research facilities for the outside users, right? So if you are interested, just you browse or simply you can contact me. So I will guide you how to make use of our facilities for characterizing your samples.
Thank you once again, sir.
Thank you, friends.
Yeah, thank you very much, Jagannathan, for these two beautiful lectures. Very enjoyable, and I'm sure participants would have benefited very much. I have just one general question. So, are you having a collaboration with industry? And you said that the actual usage of this hydrogen fuel cells, etc., is at least a decade away. So, are you collaborating with some industry?
No, sir. As of now, we have no collaboration with the industry, but for academically, we have a lot of collaboration with both nationally as well as international laboratories. But industry, because as hydrogen energy is concerned in India, very few players. It's a just now industries talking about the hydrogen.
What is the situation in other countries? How far have they gone?
Sir, in other countries, the fuel cell technology is almost it's well established, but still there's a lot of issues are there. Even recently, a couple of days back, the Elon Musk, so who is the founder of the Tesla car, has criticized this hydrogen-based technology, particularly the fuel cell, right? Because he is focusing on the EV, electronic vehicle. So this is going to become a competitor for his business. As I mentioned, that it's a geopolitics, and then but the politics are also playing a greater role to pushing down the hydrogen. So in foreign countries, it's a slowly picking up, but the industries as well as the technologists are divided about the hydrogen as well as EV. So few people are, many of them are supporting EV. So only few academicians and the companies are in favor of hydrogen. But around the globe, for the past 6 months, a tremendous interest have been shown for the hydrogen gas generation. Even in India, the Reliance and then Adani, Indian Oil Corporation, they have shown a lot of interest to produce hydrogen, but not through the process I had explained. So they are going with the blue hydrogen generation, again by using the fermentation process, or it's a gas reformation, or it's a gas-based production of the hydrogen gas. So again, that will produce a lot of greenhouse gases. I think there is a company, so in Mumbai, so they are making a small type of alkaline-based electrolyzer by electrolysis process to split the water, right? So in fact, we have filed a patent to split the it's a seawater. So using NBS2 and silicon based electro catalyst. So a couple of months we have filed it. There is a it's a great challenges are there, but still there is a great future for this hydrogen based energy technology, sir.
Yeah. So when it becomes when it comes to actual usage, the cost will get reduced so much for transportation. So that will be a great help.
Yes, sir. Only the mass production will bring down the cost.
Yeah.
Okay.
Thank you very much.
Thank you, sir.
Thank you for such an interesting session, sir. We'll start the next session. I invite Dr. S. Manivel, Assistant Professor, to introduce our speaker.
Good evening to one and all. The man of inspiration, ecstasy, and esteemed motivator. He completed BSc Honors and MSc Physics from University of Delhi and PhD Physics from Brandeis University, USA in 1970. He was a postdoctoral fellow at Tata Institute of Fundamental Research from 1971 to 1974. He joined IIT Madras as a professor of physics in December 1980. Before that, he joined as a scientist at Indira Gandhi Center for Atomic Research, Kalpakkam from 1974 to 1980. He is currently adjunct professor in the Department of Physics, IIT Madras. And also, he has been acting as visiting professor at several abroad institutions. He has given 7 video courses on national program on technology enhanced learning under Ministry of Human Resource Development, who is none other than today's resource person, Dr. V. Balakrishnan, former professor, IIT Madras. Welcome you, sir.
Am I audible now? Can you hear me?
Yes, sir.
Just a minute.
Yes, yes.
Yeah, I'm just trying to unmute myself. Yes. Am I audible now?
Yes, sir.
Let me share screen. I need to mute my video just to save bandwidth. All right. Are we ready to start? May I start?
Yes, sir.
In this lecture, in the previous lecture, we heard about some fundamentals of equilibrium statistical mechanics, namely the statistical mechanics of systems which are in thermal equilibrium, where there is no time dependence for the average values or higher moments of macroscopic physical observables. The subject of non-equilibrium statistical mechanics is not as well developed as that of equilibrium statistical mechanics. In some sense, it's because the number of possibilities here is much, much larger, and you have to be much more specific about what kind of systems you're talking about. On the other hand, there is one problem which has been sorted out and solved, starting practically with the beginning of the 20th century, Einstein's monumental work on Brownian motion. And that has to do with the way a system approaches equilibrium. It's not in thermal equilibrium, but a little close to thermal equilibrium. And the question is, how does it approach equilibrium? In the model we'll choose, an even simpler one, we ask the following question. Given a fluid in some container, in some region, V or volume V, these fluid molecules are moving around inside, colliding with each other and interacting with each other. We could ask the following: what is the equilibrium distribution of velocities of the molecules in this fluid? That's number one. And number two, if I start with a given molecule in a particular velocity state, if I catch hold of one of the molecules, for instance, and it starts off with some velocity V0, how long does it take before it reaches thermal equilibrium in the sense that it becomes part of the Maxwellian distribution? That's a valid question to ask. And it turns out to be an incredibly hard one to answer because of the problem of timescales in the problem. The fact is that if you look at the nitrogen molecules in this room, for instance, at normal temperature and pressure, the number of collisions a molecule suffers per second is of the order of 10 to the 12 or 10 to the 13. In other words, the time between two successive collisions is of the order of picoseconds. On the other hand, the macroscopic, the kind of experiments you would do on it would be on much, much longer time scales. So we could ask the following question: instead of looking at an individual molecule itself, which is the same size as every other molecule, suppose we put in these dots represent colloidal particles suspended in a fluid of molecules of much smaller size than the mass of the particles that are put in. So let's suppose that the mass of the particle put in is m, and this is much, much bigger than the mass of a molecule. Can we then make some statements about how this system equilibrates, in the sense that how do these particles, these larger particles, colloidal particles, move around? And this is the question that Einstein answered when he studied Brownian motion, which, as you know, is precisely got to do with the motion of such colloidal particles, crushed pollen grains in water, which was studied first by the botanist Robert Brown as far back as 1827. It was not understood properly then, but Einstein's monumental and seminal work in 1905 clarified the issue and set the stage for the beginning of non-equilibrium statistical mechanics. So this is the question we are going to answer, but in a very simplified manner, and we will make certain assumptions there, which will be justified as we go along by the physical numbers that are actually involved in this problem. So I start by saying, let's take these molecules here, these larger particles, a tagged particle, and I fix my attention on any one of them. And let's say that at time t equal to 0, its velocity is given by some number v0, which is measured by me. So initial velocity of the tagged particle is equal to v0, say. Actually, v0 should be a vector because it could point in any direction, but we'll make life even simpler and take any one of the Cartesian components, say the x direction, and deal entirely in terms of components rather than vectors themselves. It just complicates it in an inessential way here in this problem. We will just do the scalar problem of one component like the x component of the velocity here. In equilibrium, these stacked particles have a velocity distribution which is given by the famous Maxwellian distribution. And that distribution says the equilibrium probability that the velocity is any value v, probability density function, is equal to m over 2 pi kt, 2 pi k Boltzmann t to the power of half, e to the minus mv squared over 2 kt. Because it's a single component, it's just a Gaussian here. If it were a three-dimensional problem, then the speed has a different distribution, slightly different distribution with a factor v squared in front. But this is what the distribution is, the Maxwellian distribution is, and we all know what shape it takes. It looks like this. It's a bell-shaped curve of this kind, and the width, the half width at full maximum, is proportional to the variance, square root of the variance. It's proportional to square root of kt over m. But now we have a different problem on our hands. We've asked the question, given at t equal to 0, velocity of the tagged particle is equal to v0. What happens as time goes along? One of the questions we should answer is, what does the distribution of velocities look like? What does the probability density function look like? If you plot v versus the probability density function of v, at t equal to 0, you're given some value v0. So it's a delta function at v0. But the Maxwellian distribution is a Gaussian distribution of that kind. I should draw this better. Let me do that. So this is the Maxwellian distribution, whereas I'm given a delta function distribution, delta of v minus v0. And this, however, is Maxwellian. So the question is, how does this sharply peaked distribution, the delta function, become the Maxwellian as time progresses? What physics governs it? What do we learn from it? And how do we deduce it? That is the problem to be tackled now. So clearly the system is not pretend that it's not in equilibrium because a single particle has a given initial state which is not in the equilibrium ensemble. But at the same time, we know that as time elapses due to collisions with the molecules of the fluid, this stacked particle will become part of this Maxwellian distribution. So how does that happen is the question. And the way we do it is an extremely straightforward method, which is to say, let's write down the Newton's equation of motion for this particle, and let's solve that equation and see what happens. So what does Newton's equation of motion say? It says mass times the velocity dot, the acceleration at any time t, is equal to the force on the particle. And these are all scalars. We're just looking at one component. So the force is the x component of the force on the particle, and that's equal to some f of t. And this comes from collisions. It's entirely due to the collisions with the particles of the fluid. And that's random, therefore, because we don't know what kind of collisions are taking place, and they're taking place completely at random. So we should write F subscript R of T to show that it's a random force. And we can solve this equation. If you tell me what Fr of T is, I can solve this equation from whatever initial condition you like. So the solution is V of T is equal to V naught, the initial condition, plus 1 over m, because I take m to the right-hand side, an integral from 0 to t dt1 f random of t1. That's the solution to this very, very simple differential equation with the initial condition V of t is equal to V naught at t equal to 0, because this integral then vanishes. So that's it. The problem is solved completely. We can now ask, what's the average value of this? So we take a collection of particles, all of which have initial velocity V naught. We average over that ensemble, that collection of special particles with initial velocity V naught, and ask, what is the average value? And I'll denote the average value with a bar on top. This is equal to the average of this quantity plus the average of the second term. The average of the first term is V naught itself, because that's a given number. There's nothing to average over. It's not random. Plus 1 over m times the average value of this integral. But please note that an integration is just a summation. And an average is also an arithmetic average, and therefore is also a summation, and two different sums will commute with each other. So the average value of this integral is equal to the average value of whatever is inside the integral. So it's equal to integral 0 to t dt1 f random of t1 average value. I'm being careful now. I'm justifying every step. So when you take the average value of this quantity, you must make sure that the average of the integral is the integral of the average of the integrand. That's certainly true. But then this is a random force, and the particle is likely to be as much hit from the front as from the back by the other molecules by the molecules in the fluid, and therefore it's reasonable to assume that this average is equal to 0 on the average. When you're in a big crowd and people are pushing you from all directions, the average force on you is 0. Although instantaneously the force is not 0, but is varying randomly in direction, the fact is, and magnitude, the fact is that on the average you don't go anywhere. So you don't accelerate anywhere, and the average is equal to 0, therefore. And once that's put in, this becomes V0 itself. Already that leads to a very suspicious, one should be suspicious about this result, because it says, if you start with some particle whose velocity is given to you to be some V naught, that velocity on the average is remembered forever and ever by the fluid, because the average value of the velocity of that particle remains V naught at all times, including as t tends to infinity, which is very suspicious. Whereas if you look at Maxwell's distribution, the average value of the velocity is actually 0. It's centered about the origin, and therefore it should be 0. On the other hand, here it's turning out to be V naught. So we are worried about it. So that's worry number 1. Worry number 2 is even more serious than that, and that's what leads us to the solution. So we have V of t is equal to V naught plus 1 over m integral 0 to t dt1 f random of t1. Let's compute what is V squared of t is equal to. If I square it and find the mean square velocity, first I square the velocity and find out what the answer is. It's V naught squared plus twice V naught over m integral 0 to t dt1 fr of t1 here, plus the square of this integral. But for the square of the integral, I better write down two different integrands so that I don't get confused. So plus 1 over m squared integral from 0 to t dt1 integral 0 to t dt2 f random of t1 multiplied by f random of t2. And now I take averages. So I put a bar on top of this. There's nothing to do with V naught squared because it's equal to its own average. It's deterministic. And here comes another problem. I need the average of this quantity, but the average of this quantity, V naught is deterministic. It's specified. It's given to me. It's not a random variable yet. Therefore, the average is just the average of FR of T1, and this is also equal to 0 on this side. So the cross term vanishes. This term, however, is a different story. The average value is the average value of the product of FR of T1 with FR of T2. Now, what are we going to do with that? We need to know what's the value of this product of two random variables, one of which is the random force at some time T1, and the other is the random force at some time T2. Well, here is where the physics comes in, that this mass, the mass of this particle that we're talking about is much larger than the mass of the molecules that cause collisions and changes in the velocity. And therefore, the correlation time FR of T1, FR of T2 is actually the product, the average of this product is the product of averages, because FR of T1 and FR of T2 are not correlated with each other at all at different times. Because these collisions are happening every picosecond or so, this stuff is changing. So the force at a later time is not correlated to the force at an earlier time at all. Or if there is a correlation, it's a very, very short correlation of the order of picoseconds. And therefore, this average is 0, except when T1 is equal to T2. Then, of course, it becomes the mean square value. So let's call it some gamma, some constant, times a Kronecker delta T1 minus T2, where gamma is equal to a constant. We'll find it, but this is equal to a constant to start. Therefore, V squared of T by this model is equal to V naught squared plus, if I put in gamma times delta of T1 minus T2, one of the integrals is done immediately, and you get gamma over m squared integral 0 to t dt1, because the T2 integral gives you just gamma, and that is equal to V naught squared plus gamma t over m squared. This is even worse news than saying that the average value of V of t is V naught at a constant value, because this says that the mean square value of the velocity of this tagged particle is increasing with time. But the mean square value of this particle multiplied by half m is precisely the energy of this particle on the average. So this is saying that if you give me a beaker of such particles, then the energy of these particles is going to spontaneously increase, or effectively the temperature of this particles is going to increase without bound as t becomes larger and larger. This is tending to infinity, completely unphysical. Therefore, this problem is wrong. This solution is wrong. Cannot be true. There's some very essential physics that we've left out in this whole process, and we got to go back and examine our model all over again. I hope you see what the problem is. The difficulty is that this model, that the force on the particle is F random, may be all right, but this assumption for this force is suspicious, but even that may be all right. It's just that this force is incompletely specified, as we'll see in a second. What is the actual issue? The issue is that if you are moving in a crowd, for instance, and you try to move in one direction, you get hit more from the front than from the back. Just as when you walk in the rain, and the rain is falling straight down, when you walk in the rain, you get more wet in front than at the back. And the reason is that more raindrops hit you from the front than from the back. And the faster you run through the rain, the more wet you get in front and the less wet you get at the back, because this differential increases. It's another way of saying that there is something called friction that goes on in this random process. And in this case, since it's a fluid, this friction is called viscosity. So owing to the viscosity of the liquid in which these colloidal particles are sitting, it's clear that the random force on the particle is made up of two components. So the first one says the equation of motion therefore should read mv dot of t is equal to, on the right hand side, two parts to the random force. There is a part which is the truly random force Fr of t, all right, plus there is a force which retards the particle and is proportional to the instantaneous velocity of the particle. These units I put m here, so I should keep m here also, times some constant gamma times v of t itself. Gamma is a friction constant. So there's a systematic part to the random force because v of t itself is a random variable. It's the output random variable. Fr of t is the driving input random variable, which is delta correlated. But there is this sum here, and the way I put the m here suggests that this gamma here is dimensions 1 over time, so that it matches mv dot on this side. Now we have a different solution altogether, because this says v of t, the solution, is v naught e to the minus gamma t, because this factor gamma v is going to produce an integrating factor e to the gamma t, plus one over m, an integral from 0 to t dt1, let's write this more clearly, t to the minus gamma t minus t1. That's the integrating factor times f r of t1. Like so. So that's the solution to this equation. And now look at immediately the improvement in the problem, in the solution. The average value v of t, averaged over all particles whose initial velocity was given to be some number v naught, is equal to v naught e to the minus gamma t, plus this term, which is 0 because the average value of Fr of t1 is 0, as in the previous case. And this average value, therefore, starts at the value v naught as it should, and tends, as t tends to infinity, it tends to 0, which is exactly what happens to the mean value in the Maxwellian distribution. So it says the average value of this particle, of the set of particles, starts at the value v naught, which is specified, but tends to 0 or tends to equilibrium value of 0 as t tends to infinity. Whenever I write t tends to infinity, in quotation marks, I should write it. This really means that t is such that t is much, much greater than gamma inverse, or gamma t is much, much greater than 1. That's exactly what this limit is going to be. When gamma t is much, much greater than 1, this damped exponential is going to tend to 0. So there is a time scale that has been introduced into the problem, which is gamma inverse. And we'll come back to that. So that's a time scale in the problem, and which is the time scale that controls the behavior of the system. What happens to v squared of t? That's even more interesting as before. This is equal to v naught squared e to the minus 2 gamma t, the square of this term, the first term here, plus As before, the cross terms vanish because the average value of the force is random force is 0. But there is a term which is equal to 1 over m squared integral 0 to t dt1 integral 0 to t dt2 fr of t1 fr of t2 average value average value like so, for which we've already got a model. So I should write this properly. This quantity, as before, is delta correlated. That's gamma delta of T1 minus T2. And that will help us do one of the integrals. But there is another factor, T minus T1 minus gamma T minus T2. There are two such factors there, and therefore V squared of T average has those factors as well. And that's the integral that one has to do. And what happens if you do this integral? The answer is quite straightforward. It says V squared of T average is V naught squared e to the minus 2 gamma T, because it's square, plus gamma over m squared, an integral from 0 to t dt1 e to the minus 2 gamma t minus t1, because you have to set t1 equal to t2 using the delta function integral. And if I evaluate this, I get V naught squared e to the minus 2 gamma t plus gamma over 2 m squared times the first term. Well, let's do this a little slowly. Plus gamma over m squared e to the minus 2 gamma t. That is this portion, e to the minus 2 gamma t. And then you have an e to the 2 gamma t1, which you have to write, do an integral over from 0 to infinity, 0 to t. And that is equal to e to the 2 gamma t minus 1 over 2 gamma, which in turn is equal to V naught squared e to the minus 2 gamma t plus gamma over m squared, 2m squared gamma here, multiplied by 1 minus e to the minus 2 gamma t. And if I combine the e to the minus 2 gamma t terms, you get V naught squared minus gamma over 2 m squared gamma. That's the first term, e to the minus 2 gamma t, plus a constant term, which is gamma over 2 m squared gamma. Things are much, much better now, because now at t equal to 0, this becomes 1, this exponent. This cancels against that, and you're left with V naught squared as you should. But as t tends to infinity, or gamma t much, much bigger than 1, this whole term vanishes, and you're left with this constant here, which is what you expect. You expect the Maxwellian distribution to be obtained with this constant sitting here. However, the Maxwellian distribution is something which is independent of time. You have to be careful here, because to find the Maxwellian distribution, I must also average over all possible values of V naught, which belong to the Maxwellian distribution itself. So if I do that, and let me call that average V squared. Oh, something's wrong with this whole thing. Excuse me. So V squared of t, average value this is equal to V naught squared average value over the Maxwellian distribution, but we know that V naught squared average value for the Maxwellian distribution is K Boltzmann T over M, KT over M, minus gamma over 2m squared gamma e to the minus 2 gamma t outside plus gamma over 2m squared gamma. And under what conditions is this going to be the equilibrium value kt over m? If it is, if gamma over 2m squared little gamma is kt over m, then you see this comes out neatly and it says that the mean square value does not change at all, or the system's temperature does not change at all. In other words, you require a consistency condition, which is precisely what we are looking for. Equilibrium distribution attained correctly if and only if gamma over 2m squared gamma is equal to kt over m, or capital gamma equal to 2m little gamma kt. Once that condition is met, there is complete consistency in our solution. So the equation we wrote down, mv dot equal to m gamma v plus f random of t, is called the Langevin equation. First order ordinary differential equation with an integrating factor sitting here. And the solution we wrote down, we took the averages and said for consistency, for equilibrium to be maintained, because we haven't done anything to the system at all, capital gamma must be equal to little 2 gamma kt. But what is the left-hand side equal to? This is gamma, the strength of the fluctuations of the force, the random force in which the particle is to which the random particle, to which the colloidal particle is subject. So the left-hand side is the strength of random force. It's a measure of the strength of the random force on the particle, or the strength of the fluctuations to which the the tagged particle's velocity is subject. So on the left-hand side, you have the strength of the fluctuations. On the right-hand side, apart from the mass constant and the temperature, this constant gamma is the measure of the friction in the system or the dissipation. So this relationship is a relation between the fluctuations and the dissipation in the system, and goes by the name of the fluctuation dissipation theorem or relation. It's the first of a whole host of such relationships, which are consistency conditions on the system. So it says the same molecular collisions which cause the velocity of the tagged particle to depart from equilibrium and fluctuate in time also help in bringing the system back to thermal equilibrium and are responsible for the maintenance of the equilibrium. It's a really wonderful, remarkable statement. The consistency condition, first found by Einstein in essence, and it's in this context it's called the simple fluctuation dissipation theorem. I might point out also that there is a connection here between the viscosity of the problem and the friction constant, because if this tagged particle is taken to be a spherical particle of some radius a, then you know that m gamma times velocity is the limiting velocity or terminal velocity, and that by the Stokes relation is 6 pi a eta v, and we can remove the v on both sides. So you really have m gamma equal to 6 pi a eta, where eta is the viscosity of the fluid. So it's a directly measurable quantity here. So this gamma is not a fictitious some arbitrary constant, but rather is directly related to the viscosity of the fluid in which the tagged particles are. And this is, of course, assuming the fluid particles, the tagged particles are spherical particles. If not, different geometries would give a different geometrical factor. I might mention here, by the way, that the 6 pi, which you know in Stokes' formula, is specific to the fact that as the particle moves through the fluid, the fluid sticks to the particle, so that the fluid on the surface of the particle itself has zero velocity. So it's called a stick boundary condition. If, on the other hand, the particle moved such that it slips through the fluid, then you must have a slip boundary condition. And for spherical particles with perfect slip boundary condition, this 6 pi changes to 4 pi. I thought it'd be amusing to have that piece of information. It's actually a geometrical factor. It's not very relevant to us. The important thing is that the friction constant gamma is directly proportional to the viscosity of the particle here. And this relation is called the fluctuation dissipation theorem. And it tells us how equilibrium is reached. So we know that the mean value drifts. The mean value starts at V0 and moves to the left such that at any given time, the mean value is V0 e to the minus gamma t, and it finally ends up at 0 here. The mean square value also, the variance is 0 at V equal to V, at t equal to 0, the variance is 0. You have a deterministic value V0 for the velocity. But the question is, what happens as time increases? It finally reaches the equilibrium value, the variance becomes kt over m and sits here on the Maxwellian. One could ask the following question: how does the Maxwellian distribution itself change from the delta function to the equilibrium Maxwellian distribution? For that, you need a little more information. You need to know that this quantity in this Langevin equation, gamma v plus 1 over m f random of t, we need to know that this is also what is technically called a delta correlated white noise, or a Gaussian white noise, delta correlated noise with the flat power spectrum. Once you make the Gaussian assumption here, then we have a theorem in stochastic differential equations which says that if the driving force is Gaussian as a random variable, its distribution functions are all Gaussians, then the output value variable v, the output random variable, is also Gaussian. This means that everything is specified about v in terms of its mean and its variance, and the distribution is as follows. P of v as a function of time now also, and the velocity, turns out to be a Gaussian, but instead of m over 2 pi kt, you have m over 2 pi kt times 1 minus e to the minus 2 gamma t. The whole thing is supposed to be taken to the power of half. This is the normalization factor for the distribution to the power of half. An exponential of not v, but minus m v minus v naught e to the minus gamma t, because that's what tracks the mean, squared, divided by 2k Boltzmann t times 1 minus e to the minus 2 gamma t. This distribution is called the Ornstein Uhlenbeck distribution. Or probability density function. It tends, as t tends to 0, it tends to delta of v minus v naught. And the same thing tends, as t tends to infinity, to m over 2 pi kt square root times the exponential of the usual Maxwellian, mv squared over 2 kt. So the distribution remains Gaussian at all times. Its mean value is at v naught e to minus gamma t, its variance goes like 1 minus e to the minus 2 gamma t times, of course, this kt over m. And it interpolates between the initial delta function and the final Maxwellian equation distribution. So this answers completely the question of what happens to the velocity of the tagged particle. We found its distribution completely as a function of time. And that's the Ornstein-Uhlenbeck distribution. We can go further. We can ask what's the physical significance in this problem, apart from the fact that it's the viscosity. What property of this velocity of this tagged particle does gamma specify? And the answer is found by computing not v squared of t, but v of t prime, average value over the full ensemble. And it's called the velocity correlation function or autocorrelation function. And a little bit of algebra says that this can be shown to be equal to kt over m e to the minus gamma times modulus t minus t prime, whichever is larger is the first term. At t equal to t prime, you can see that v squared at t equal to t prime, you settle, becomes a mean square. That's equal to kt over m. So that takes. On the other hand, v of t prime average tends to 0 as mod t minus t prime tends to infinity. In other words, if the separation of the time arguments is larger and larger, the system loses the memory of its initial state, and this whole term kind of goes like the average value of v of t times the average value of v of t prime, because the memory in the system is precisely specified by gamma inverse. So gamma inverse rather is equal to the velocity correlation time. And we've already seen that it's directly related to the viscosity of the fluid. And therefore, we can measure it. We can measure this time. And it turns out that for the colloidal particles we are talking about, this gamma inverse, the mean time between collisions is, namely the correlation time of the random force itself, is of the order of 10 to the minus 12 seconds. On the other hand, gamma inverse in general in these situations is such that gamma inverse is of the order of 10 to the minus 6 seconds. So 6 orders of magnitude separate the tagged particle's dynamics from that of the molecules in which it's immersed. And this separation of time scales was first appreciated deeply by Einstein, and that is how the whole theory got set up. And this whole Langevin model is feasible simply because of that fact. It is because of the fact that you have this very clear separation of time scales in the problem. In fact, there is a time scale shorter than this also of the order of 10 to the minus 15 seconds. And that is the electromagnetic interaction time between molecules. They interact with each other with van der Waals forces, which are electromagnetic in origin. And the time scale typically of electromagnetic interactions, the collision time, if you like, is of the order of 10 to the minus 15 seconds. The mean time between collisions is of the order of 10 to the minus 12 seconds. And the mean time for the autocorrelation velocity of the particle to remember its earlier velocity is of the order of a microsecond, 10 to the minus 6 seconds. Is there a time scale beyond this? And the answer, of course, is yes. Any time t much greater than gamma inverse will be in what is called the diffusion regime, and I will come to that in a second. So there are 4 time scales in the problem, and the crucial one is this, where the Langevin model applies here, and this follows as a limiting case. It's called the diffusion regime. So this beautiful separation of time scales in the problem is what enabled this particular problem to be solved. Now, what can we say about the distribution function itself? We've already written down what it is. It's the Ornstein-Uhlenbeck distribution. But can we write an equation for it and solve it? The answer is yes, once again. So let me introduce that equation to you, just for the sake of completeness. P of v comma t satisfies the so-called master equation. master equation. It's a Markov process V, and it satisfies the master equation given by delta P over delta V in delta T is equal to gamma times delta over delta V times P plus gamma KT over M delta 2P over delta V2. This is called the Fokker-Planck equation in this case, for this particular problem, or Langevin equation. Whenever you have a Langevin type of equation for a random variable, you have a corresponding Fokker-Planck equation for the probability density function of that random variable. And this is what it is in the case of P. Now, the equilibrium distribution can again be obtained from this as a solution. Maxwellian distribution can again be obtained as a solution if you set delta P over delta T equal to 0. What happens in that case? Well, it will satisfy, the equilibrium distribution will satisfy d over dv, because there's no t dependence now, v times p equilibrium plus kt over m d2 p equilibrium over dv2 is equal to 0. And that, without much difficulty, can be shown to have a solution p equilibrium equal to the Maxwellian distribution in equilibrium. This becomes an ordinary differential equation. There's no time dependence. This quantity vanishes and you're back to the Maxwellian distribution. But the general solution is the Ornstein-Uhlenbeck solution. Is the solution. So much for the velocity, and there are various modifications of this Langevin equation, etc. So the moral of the story is this approach to equilibrium in this problem is well modeled by the Langevin equation and the associated Fokker-Planck equation for the probability density of the velocity of the random variable, whose solution is the famous Ornstein-Uhlenbeck distribution. But can we say how far the particle has gone? Where does it actually go and how far does it go? That's an interesting question to ask, and we're going to answer that next. So let's see what the displacement of the particle does. But the displacement x at any time t minus x at time 0, this is the displacement. By definition, this is equal to the integral of the velocity of the particle dt1 v of t1. That's by definition true. That's the definition of the displacement of the particle, just the integral of the velocity. Now, what's of interest to us is the mean square displacement of the particle, because the displacement itself on the average will be 0, as we can see. So what is the average value of x of t minus x of 0 whole squared equal to? From this integral, we need to find out what this is. And that's not very, very difficult. It's a little more difficult or complicated than the mean square. So we have mean square displacement is equal to, by definition, x of t minus x of 0 whole squared is equal to, if I take the mean square of whatever I wrote down earlier there, it's equal to an integral from 0 to t dt1, integral 0 to t dt2, times what was inside the integral was v of t1, v of t2, essentially. So we need to write that down and take its average, v of t1, v of t2 in equilibrium. And what in turn is this equal to? This is equal to, remember what we already found for the velocity correlation, it's kt over m, integral 0 to t dt1, integral 0 to t dt2 e to the minus gamma modulus t1 minus t2. This is a simple integral to solve, but it's double integral. You've got to be a little careful. The integrand has t1 minus t2 if t1 is bigger than t2, and t2 minus t1 if t2 is bigger than t1. So one has to be cautious in doing such an integral. Here, we draw a little picture with t1 on the x-axis and t2 on the y-axis. This integral is over a square, which stops at t on both sides. And the integrand is completely symmetrical. In other words, it's a function of mod t1 minus t2. So it is reflection symmetric about this 45-degree line. And the value of the integrand at any point here is the same as the corresponding value at the reflected point here, which means you can write this as equal to twice kt over m integral 0 to t dt1, an integral from 0 up to t1, because t2 is less than t1 now. We're going to take this segment here and integrate over this and multiply by 2 dt2 e to the minus gamma, just t1 minus t2, no modulus sign. We have to do this double integral, which is not very hard to do. And when you do that, you discover the answer is twice kt over m gamma squared. Inside you have gamma t minus 1 plus e to the minus gamma t. This is a well-known function. It's called the Lambert function. This is what the answer is finally. And what do we do with it? Well, we can take various limits. So mean square displacement is equal to twice kt over m gamma squared. Gamma t, dimensionless number, minus 1 plus e to the minus gamma t. What does this function look like as a function of gamma t? That's interesting to ask. So I plot gamma t here, and I plot this function here. Well, for small values of gamma t tending towards 0, you can see that the leading term in the exponent here, e to the minus gamma t, goes like 1 minus gamma t, which cancels both these terms. The next term is proportional to t squared. So it has got to increase like a parabola out here. And asymptotically, as gamma t becomes very, very large compared to unity, the exponent can be dropped. And the leading term is essentially gamma t here, nothing more than that, which is a linear rise. So it's clear that there is a linear rise like this with a certain slope, and this function starts off like this and tends towards that in this fashion. So the behavior of this function at gamma t much, much greater than 1, the leading behavior goes like twice kt divided by m gamma times t. And those who are familiar with the diffusion equation will realize that this is nothing but the diffusion term twice dt, where this is the diffusion coefficient or constant. So we have another valuable lesson here, which says that in the diffusion regime, which is here, this regime where gamma t is much, much greater than 1, the behavior of the mean square displacement is linear in time. That is precisely characteristic of diffusion. And d in this problem is kt over m gamma, which is also kt divided by 6 pi a eta for spherical colloidal particles. This is the famous Einstein-Sutherland-Nernst relation, which helped Jean Perrin to actually measure the mean square displacement in an ultramicroscope of colloidal particles, verify Einstein's theory of Brownian motion, and discover what the value of this d is by putting in this equation here. And substituting in this equation, you can actually find the value of the large number like Avogadro's number, or conversely, on the other side, the size of very, very small particles. This was Einstein's motivation. He wanted to show that you could not only measure molecular sizes, but you could also measure Avogadro's number, a very large number and a small number. using this technique. So it's directly experimentally verifiable. And this relation is due, I don't exactly remember who are all the people associated with it. So certainly Einstein, Sutherland, and possibly Nernst as well. Etc. Yes. So this problem is completely solvable. Oh, one could also ask a final question. We found the mean square displacement. If I call delta x the displacement, what's the correlation time? What's the correlation of the displacement itself? What's the autocorrelation of the displacement to? Delta x t1 times delta x t2. That can also be computed, and I won't do that here. It's a lengthy expression which you get on the right-hand side, which reduces to the mean square displacement at t1 equal to t2. So this kind of gives you a bird's eye view of the Langevin equation, the Fokker-Planck equation, the approach to equilibrium in this particular Langevin model, a little bit of information about what Gaussian processes look like, and so on and so forth. So I thought this would be a useful appendix or addendum to the standard statistical mechanics courses here. This is actually the starting point of non-equilibrium statistical mechanics, and the subject takes off from this point. So this is all I have to say at the moment on this, and if there are questions, I'll take them. Thank you.
The session is open for discussion. Participants are requested to post your questions in the chat box.
As before, somebody will have to read this out to me.
Shall I read it out for you, sir?
Yeah, would you mind doing that? Thank you very much. Yeah.
Sir, Professor Leonard Susskind turned his lecture series at Stanford as the theoretical minimum series books. I request you to print your lecture series in the form of books. They surely benefits the physics community. Please.
It's very kind of you to say that. It's a monumental task. I'm not sure if I'm capable of it. I do have some books on it. For instance, this material I talked about today, I have a book on non-equilibrium statistical mechanics published a few years ago called Elements of Non-Equilibrium Statistical Mechanics. And then I have a fairly comprehensive book on mathematical physics with emphasis on the physics part of it. So a large amount of material found in those NPTEL lectures and some of the courses is already in that book there. So I have made some efforts, although I don't feel competent to write a series of books on all of theoretical physics. That's also very different altogether.
Next
so
one.
Yes, yeah.
Please suggest some useful references to dwell the topic in detail.
As I said, there is a book that I have written called Elements of Non-Equilibrium Statistical Mechanics, which contains all this material. There are many other books on it as well. The famous book by Landau and Lifshitz on statistical physics has a chapter on fluctuations, which again is a very useful thing to do in the context of linear response theory. And there are books on equilibrium as well as non-equilibrium statistical mechanics. There's a very large number of textbooks which you can find on the internet if you search. You can do that. Yeah.
Thank you very much, sir, for such an informative session. Participants are requested to join the valediction.
So before closing, let me thank Bala once again for your very beautiful these two lectures with the characteristic clarity of yours. Thank you very much for all your efforts.
Thank you.
Thank you.
Participants are requested to wait for a few more minutes.
Maybe I can stop sharing.
Yeah, you can stop sharing.
Oh, now I see the chat box. I couldn't see it earlier. I was wondering where it was. But, must have been quite difficult running this sort of program during the COVID times.
Yeah. Yeah, I think Dr. Ravichandran made all the arrangements. So we should be all thankful to him. Yeah.
Sir, please tell me, sir.
Yeah.
Sir, we are preparing for the validatory function, sir. In another few minutes, we'll start it, sir.
Yeah, sure.
I seem to have ended before time. I was not very sure what the time factor was, but
Just a couple of minutes.
better early than late. And also have to leave in a short while. Lakshmanan, I'd like to leave if I may, because I have somebody coming in at 4:30. I have to request you to excuse me because I'd asked somebody is supposed to meet me at 4:45, but then he's just called and said he'll be here at 4:30, so I might have to leave.
Oh, okay. Okay, please. Yeah.
So, thank you very much once again for the warm hospitality and the opportunity. We'll see you sometime. So, yeah.
Thank you, Amit, sir. Thank you, sir.
Welcome. Welcome. Thank you so much.
Thank you, sir.
Good evening, everyone. We'll start the valediction. I invite Dr. J. Geeta Priya, Assistant Professor, to deliver the welcome address.
Good evening to all. At the outset, I am privileged and honored to offer a formal welcome address. I welcome Dr. R. Sundararaman, Principal, National College, who is presiding over this valedictory function with his presidential address. I extend my hearty welcome to Professor Dr. M. Lakshmanan, Bharatdas University, Trichy, convener of this workshop, and the other resource persons, namely Professor G. Bhaskaran, the Institute of Mathematical Sciences, Chennai, Professor B. Ramakrishnan, Indian Institute of Science Education and Research, Trivandrum, Professor V. Balakrishnan, Indian Institute of Technology, Madras, Professor K. Jaganathan, Bharatdas University, Trichy, Dr. R. Sankaranarayanan, National Institute of Technology, Madras, without whose expertise this workshop could not have succeeded. I record my sincere welcome to Dr. A.T. Ravichandran, coordinator of this workshop, whose leadership ability caused the success of this 3 days program. I am happy to welcome Dr. S. Pari, head of the department, whose cooperation played a major role in organizing this workshop. I also welcome my dear colleagues of the Department of Physics, National College, Trichy, fellow teachers, research scholars, and the enthusiastic students whose participation enriched this program. I further extend a warm welcome to our supporting staff of National College, Trichy for their sincere dedication in making this workshop a grand success. I welcome one and all. Thank you.
Thank you, ma'am. Now I request Dr. R. Sundararaman, Principal, to deliver the presidential address.
Professor Lakshmanan, Dr. A.T. Ravichandran, Dr. Pari, Dr. Geeta Priya, research scholars, resource persons, faculty members, and my dear students. Good evening to everybody. Physics is a fascinating science. The subject matter is powerful and all pervasive. Whether it is energy or light or power or force, everything is conveyed by physics. Further, physics explores diverse forms of energy, static energy, kinetic energy, and so on. Mechanical engineering is based on physics. Everything that moves, from the simple bicycle to bullet trains, airplanes, and even rockets, are driven by the principles of physics. In the field of communication, radical and violent changes have taken place due to research in physics. Optic fiber technology, satellites have changed the way we communicate. At any given moment, at least half the population is looking into their cell phones, which are developed because of scintillating advances in the field of physics. The role of laser is widening, and its applications in the medical treatment are a boon to mankind. The all-pervasive physics makes life comfortable and joyful. Most interesting aspect of physics is that it is a bottomless gold mine. It supplies new and better products and services year after year, month after month, and day after day. For example, nanotechnology has helped to develop new materials which are functionally efficient and economically advantageous. New developments are taking place and new branches sprout from classical physics. It is a beautiful and interesting process. Quantum physics is the study of matter and energy at the most fundamental level. It uncovers the properties and behaviors of the very building blocks of nature. Every branch of physics remains very dynamic. Academicians, researchers, and students of physics have the wonderful opportunity to explore the hidden, mysterious, and grand potential of physics. I am happy that Department of Physics is providing a platform for enhancing the knowledge of all teachers, researchers, and students. I congratulate the convener, Dr. A.T. Ravichandran, head of the department, Dr. Pari, faculty members, and students for organizing the workshop. My hearty appreciation and best wishes to every one of you. Thank you very much.
Thank you, sir. I invite Professor M. Lakshmanan, convener of this 3 days virtual workshop, to give remarks about this workshop.
Respected principal, colleagues, and my dear young friends. As the principal remarked, physics is fascinating. Dr. Ravichandran, under the support of the head of the department, Dr. Pari, and the colleagues from the Department of Physics, has organized a very interesting lecture workshop for the benefit of young people, young students, scholars, and the teaching community as a whole. In this 3 days lecture workshop, we have seen some of the leading experts speaking on different topics in physics in their own characteristic style. Just now we saw delightful lectures of Professor Balakrishnan, and then in the forenoon we saw the very fascinating lectures of Professor Jagannathan and Professor V. Ramakrishnan. Earlier in the 2 days, we saw Professor Sankar Narayanan and Professor Bhaskaran speaking on some of the very interesting topics. So I do hope that these lectures from different perspectives, covered a wide area of significant part of physics, which I hope clarified some of the existing topics, but also pointed out newer areas of research and exploration, particularly for the young people, the students and scholars, to pursue in their career. I do hope that all of you will take up some of the topics that have been covered during these 3 days in your future career. We are all extremely thankful to the 3 National Science Academies for providing necessary support for the organization of this lecture workshop. I once again thank the management of National College, the principal, the head of the department, and all the colleagues from the Department of Physics of National College, and in particular, specifically, I thank Dr. Ravichandran for having taken up this task of organizing this lecture workshop during a very difficult time. We thought just a few days ago that we have almost overcome this pandemic, but now, just now we saw that it's again starting up afresh. But I do hope that in the shortest possible time in future, we will overcome this temporary difficulty and we will continue our academic pursuit with full vigor. I wish all of you all success in your endeavors. Thank you very much. Thank you.
Thank you, sir. I invite Dr. A.T. Ravichandran, Associate Professor and Local Convener, to present the report of the workshop and propose the vote of thanks.
Good evening to everyone. The 3 days virtual lecture workshop on recent developments in classical, quantum and condensed matter physics, organized by PG and Research Department of Physics, National College, Tiruchirappalli, and sponsored by the Indian National Science Academy, New Delhi, the National Academy of Sciences, Allahabad, Indian Academy of Science, Bengaluru, went on very well. More than 400 participants from all over the country registered for this workshop and nearly 1/4 attended regularly. We could understand the difficulty in attending a day-long online program. Network issue, power and bandwidth are very important for a seamless participation. First of all, I would like to convey my gratitude to Professor Lakshmanan for his wonderful guidance and support in organizing this maiden virtual lecture workshop. Thank you, sir. I am grateful to all the speakers, Professor Lakshmanan, Professor G. Bhaskaran, Professor V. Ramakrishnan, Professor V. Balakrishnan, Professor K. Jagannathan, and Dr. R. Sankaranarayanan for their immediate acceptance. Their excellent and brilliant lectures on various aspects of theoretical physics motivated the young students, research scholars, and faculty members. We had a discussion session after every lecture that shows the level of involvement and spirit of participation. I thank the 3 Academies of Science and the Science Panel for the approval and financial support to conduct the 3 days virtual lecture workshop in a successful manner. I thank all the participants for their excellent participation and fruitful discussion. I record my sincere thanks to Mr. Kannan, Kaho Infotech for the online platform, and Mr. Sasikumar, our college network engineer, for his technical support to organize this workshop successfully. I thank our college management, Secretary Sri Raghunathan, Principal Dr. Sundararaman, HOD Dr. Pari, staff members, both aided and unaided sections, research scholars, support staff, and present media. Last but not least, I thank everyone for this wonderful support in organizing this 3 days lecture workshop successfully. Thank you very much. Thank you.
Thank you, sir. I request the participants to kindly fill the feedback form. Thank you.
Thank you, sir. Thank you for your support, sir. Support,
Thank you.
guidance, sir.
Thank you. You can leave. Thank you.
Dr. Ramakrishnan, sir, thank you very much for your support. Dr. Sankaranarayanan, thank you very much for your excellent lectures, sir. Thank you, sir.
Sir, thank you so much for giving opportunity. Thank you.
Thank you, sir. Thank you, Mr. Thanks. Answer.